as well. So I'm
Perfect.
excited. Yeah. So if you want to do me a, oh yeah.
All right, and it looks like we're back up and back to going.
Fantastic. I appreciate it. And so you had mentioned that you were a you were a moderator. Is that correct? Mediator.
Yes.
Awesome. Can you remind me what the code was for that? Because I'm an ENFJ.
I'll just get that. And while I'm pulling that up,
Yeah.
I think being a introvert, I think I'm more of an introvert with like some quote unquote extroverted tendencies, as
Yep.
like they'd say. And I think the code is INFPA/INFPT, if that's what you're looking for.
Yes.
Okay.
Awesome. All right. And so in terms of being an INFP and being in the middle of a presentation, I'm really glad that we're back on stream. And my husband is trying to call me, and so I'm just letting him know I'm going to try to call him back at this point in time. So hopefully everything is good to go. We talked about extroverted and introverted, right? And so one of the other pieces that you and I align on is this where we direct our mental energy, right? And so depending on, kind of how you answer these questions and things like that, some people in the world kind of like observe things around them. And, they're really kind of like, I'm going to like monitor what's going on in the world around me and kind of use that to help make decisions and have these different pieces that come into play, right? So they're more observant. Whereas you and I, we'd be considered a little bit more intuitive, right? And so it's kind of like the ability to pick up on things that aren't necessarily something you can see with like the naked eye. So a lot of times working with the engineers, they're much more observant than I am, but like I can pick up on like some more of the feelings or some more of the dynamics that are happening within a room. And so as that happens, what you might see is, people who are intuitive are kind of like, tapping into that, like, well, what's happening here? Or like, that feeling of tension that people might see. It can be really hard if someone is very, very observant to be able to kind of explain that intuitive piece. It's like, if someone who's observant is just like, well, but I don't understand why you don't see it this way, because this is literally how I'm viewing it, and it's very black and white. Whereas from an intuitive point of view, it's like, it's a gut check. It's like, does this feel correct? Like, it just doesn't feel right. Like there's something, about this that, I'm looking at all the data, but it doesn't feel right. And so those different pieces are really important to remember, because if you're starting to get into conflict with someone, honestly, what's really interesting is you might be trying to reach this like same goal up here. But if you guys are going, but you are coming from two different places, like ultimately the goal is the same, but if you're kind of coming from these different places, your ability to understand each other is compromised. And so if you're able to kind of like take a step back, realize, hey, I'm missing, their point. Like we're doing these same things here. We want to be here. How can I work backwards and, kind of figure out a way to encourage people to see not only my point of view, but how can I see their point of view? So that's generally what I do between the intuitive versus observant pieces as well. Any questions about that?
No, not a bunch of questions at all.
Excellent.
Other than just statements about how I think both are pretty important.
They are really important. Absolutely. And then, I mean, in terms of, thinking versus feeling. So that's kind of the next piece as well. And again, we're generally aligned on that from a feelings point of view. And a lot of times you can be like 50-50. And if something major happens in your life, it may also change the way you think about these things. Like, I mean, back when I was more so in high school, I would, pop up as, an adventurer, right? And so I was a lot, I was very feeling oriented, but, I was more flexible and kind of go with the flow and kind of like, life of the party. And then as I got older, I started becoming a little bit more analytically oriented, but a little bit more towards the, well, how can we make big social change? And how can we work together to do that? And so as you go through life, these pieces will change, and it's just kind of fun to kind of watch how you've developed. And in certain instances, like if you take this at work versus you take this like when you're with your friends, you can get different answers because you're in a different mindset. It's very interesting. But this idea of thinking versus feeling, I think that one's pretty obvious. It's just how do you make decisions or cope with emotions? If you're a feeling person, again, you're going to kind of go with like, oh, well, what does my heart say? Like, what are these different pieces? If you're a thinking person, you're going to be like, literally thinking through these various pieces and trying to process the information in a way that allows you to have that analytical capture and that mindset that you're able to apply. And then finally, in terms of tactics, like how you approach your work, I can always flip between judging and prospecting. Like right now, I'm more in this like judging area, but it's basically how I make decisions, right? And so, from a judging point of view, it's like having everything aligned in a row and put together is something that I really appreciate. But from a prospecting point of view, you would be better towards the like, I'm going to go see what is available. And kind of you can see these different opportunities. And if something isn't like set into stone, you're able to kind of react a little bit more cleanly to disruptions from that point of view. And so I always kind of like from the judging versus prospecting point of view, if I'm in an event season, I tend to skew more towards judging because like everything's on a schedule. Whereas if I'm able to be a little bit more creative and be a little bit more, involved with the community, I'll skew more towards the prospecting piece, which is always kind of fun. So, and then finally, so like in 16 personalities, you get this bonus piece, which is either A or T, assertive or turbulent. And what is fascinating is I've actually found that when I have younger high school students do this, they'll come out with turbulent because this is all about your confidence in your abilities and the decisions that you make. And so as you get older, it starts skewing more towards assertive. At least with young women, that's what I've kind of, started seeing. And so it's a really interesting way to judge how confident you are in what you're doing and to kind of identify if you're having any self-confidence issues as well. And so knowing all that information really allows you to kind of sit there and say, okay, you tend to be more of a prospecting individual, and I'm more of a judging individual. And what that means is, if I come to a meeting, if you come to me and you're like, let's change the plan and throw it out the door, my immediate reaction is probably going to be like, what are you talking about? And like, I freak out a little bit. And so knowing that allows you to reshape the discussion you have with me, right? So for instance, because, I was a little bit more of the, like, okay, I'm going to throw the student board of directors meeting together. I'm not going to give them agenda and we're just going to wing it and it'll be fine. And I don't normally do that, but that's kind of what I did in this instance. What I discovered after having all of my student board of directors information and 16 personalities and Myers-Briggs information was, oh boy, they really like when they know exactly what's happening and when they have a schedule so that they're able to think and respond to things. And so from that point of view, I started literally making schedules, and like instead of it being more ad lib and off the cuff, I purposefully structured it so that I was able to support them to the best of their ability. So yeah.
Well, yeah, I know. I definitely at times love structure because if I'm running into something, I just sometimes I just love that strict line, working to the line. But then sometimes when you're in the moment, you just got to throw something together. It's in the heat of the moment. You can sometimes just come up with something like so amazing.
Absolutely.
Do you think that's been maybe one of the biggest challenges was like trying to figure out how to mediate the two of them and just come to like a decision of like how specific people work together?
Yeah, no, and that typically is a challenge. The other challenge is normally around nature, like how people make decisions and cope with emotions. So that thinking versus feeling, again, something that I see very often in my engineer friends that I have. And so typically what I do there, and even what I do in any of these other areas, is I kind of, if I realize I'm starting to get into what seems like an argument, what I try to do is kind of say, whoop, I realize we're getting into an argument, but are we just loudly talking about the same thing and we agree with each other, but we're just kind of going back and forth? And so what I'll try to do is like take a step back and like go a higher level, right? So get out of the weeds, get out of the grass, and like look at the 1,000-foot view and say, okay, and listen, right? So being an advocate is all about listening. And so, listening to how they are thinking through this process, what they're thinking about, why their thoughts kind of align in this direction, that to me kind of helps me process like, okay, I normally react with feelings, but I got to have the like analytically oriented thought pieces behind this process to ensure that people understand where I'm coming from and they don't just think I'm making like this gut reaction, even though my gut reaction is backed by what I think is, the solid data. Does that explain your question? Are there any other questions that came from that?
I just got a quick question on the side. Someone just asked me real quick, like, what inspired you to do this?
Like the presentation or the
like,
16?
I'm just assuming the question's based on like how did you, other than like the Myers-Briggs test and like applying that, like what inspired you to like just put together such like extravagant ideas and then just like fixate it onto like a specific point?
My gut reaction, so I'm going to say it because like normally I'm not this confident, and I think my husband would be very proud of me, so it's like I'm just that awesome. Okay, now having said that, so I realized that I worked with a lot of people who were kind of similar. Like they weren't similar to me, but like their kind of personality and the way they thought about things was really valuable. And so I was trying to learn more about why me and this one volunteer, we were always just like so well in sync. And I was like, I don't understand. So I literally was just like, I've done the 16 personalities before just for fun. Like randomly. And I was like, okay, do this test for me. And so they did it, and they ended up getting, I ended up getting this description of them and like their background and the different ways they think about things. And I was like, that's dead on, that's dead on, that's dead on. And I kind of realized that they were plugging a lot of the like holes that I had. They weren't quite an opposite, like we complemented each other. But it was kind of this way of thinking that I hadn't seen before. And so I was just like, okay, this makes a lot more sense. Like, I work really well with these types of people because I can see a big vision, but they can go execute on it. And so being able to find more people like that is kind of cool. So when I joined Reinvented, I became the chief operations officer, and I, started really enjoying this, 16 personality stuff and things like that. And so what I did, and actually even before that, what I did is once I found out this one volunteer's information, we were having some volunteer challenges, not big challenges, just like miscommunication. And so I had all of my volunteers go through 16 personalities. Like my key volunteers go through 16 personalities. And then I like sorted it based on like information and area. And so I'm able to kind of like zone out these different things and understand how my volunteers skew in one direction or the other, so that I could kind of strategically appeal to their, their thinking pieces, their thoughts, like, some of those different aspects as well. Oh my gosh, conserving energy, right?
Definitely conserving energy.
Yeah, a little bit more. There we go. So, like I actually started pulling this together, and then I sat down and I was like, this is fascinating. And because I'm building a team on Reinvented as the chief operations officer, at first I was interim COO, then I accidentally got sucked into just being the COO as a volunteer. And so I'm still here. Like it's been a good solid 9 months. And I was like, COVID happened, so I'm bored. So why not pick up something? But I have every single one of my staff members go through this so that I can pull them all together and I can kind of, see what skills are coming to the table and what personalities are we missing? Because when you have a more diverse group of people who have different ways of thinking and have different backgrounds, different genders, race, ethnicities, etc., you are able to have a more enriching and powerful discussion. And I think that that's important. And so I not only use this information to build a team and understand how to best work with a team and teach them and grow them as a mentor, I also use it as a way to say, I don't have these types of people on my team, and I really want to find someone who's more of that analytically oriented pieces. It also helps because like I realized we had an analytically oriented volunteer and I put them on data analysis for impact. And it was a wise life choice because they were really able to like get excited about it because they appreciated that like detailed oriented like breakdown piece. And so that's just again another example of like how you can kind of use some of this information to make amazing decisions or good decisions for your crew. So, are there any other questions?
Well, I don't think we have any questions in the chat in the moment, but I definitely just want to say, even though you might not want to state it, I do think that so far you were pretty amazing. I just want to get that out of the way.
Oh, thank you. So I do have one more piece that I wanted to share as well, since we're having an advocacy presentation, and this ties in really well. So one of the programs that I've started working on with Sarah Heimlich and Luann Heimlich and Lori Shimizu from Minnesota, Christine from California, et cetera, is this First Female Leaders group. And so it's essentially First Female Leaders for Alumni and Mentor Empowerment, turned into the acronym FLAME. Very exciting. And so what was interesting is we essentially, came together. And as an advocate for young women in STEM, one of the big things that I've noticed in the first program is that when there are opportunities to recognize mentors and have people come together, a lot of times you have these amazing male allies and mentors and people coming together who reflect this like similar demographics, and there is very little diversity. And I was frustrated with that, and so something I did last year is I kind of made this appeal to strong female identifying women in the FIRST community and invited them to come to Indiana and be judges. And I also strategically looked at my volunteers, and I realized that my robot inspectors, some of the reasons that I get a non-diverse group of robot inspectors was because I was scrambling to fill that role at the very end. And so instead of scrambling to fill it at the end, I identified female identifying young women in college who are freshmen or sophomores or even beyond, and actually took the time to reach out individually and invite them to become robot inspectors. And I don't even know how illegal this is. So like, if anyone from HQ is watching this, like please ignore this part or mute or, cover your ears. But I even gave them like bows, like clip-on bows that were the same color as the hats, because then people could choose, right? Do you want a robot inspector hat or do you want like a robot inspector bow? You can get, both or either. It doesn't really matter. But it was just something that was like, well, we're offering female cut, clothing for judges now, which is great. Or lady cut clothing. I don't know. I think they should just call it slim cut and like standard cut, because like, yeah, that would be better in my opinion, but it's fine. So anyways, so I had started doing all this work in Indiana, and I had made this pitch, and I said, I want the future city of FIRST to be a place where women can thrive, because I was tired of kind of sitting down and hearing from these students that they weren't necessarily in an environment that allowed them to expand their technical skills because of unconscious bias that people didn't know how to address. So because I did a bunch of this work, and we've talked to these people, and everyone who knows Sarah knows that she does amazing things and invents stuff out of thin air, along with her crew and her mastery, the master of teams behind her and people who think that she's great. And so when she came to me and she is like, Renee, I want to solve this problem. Like, I think we need to get a group together and build a community where we can have this network to ensure women can thrive, and we can highlight these mentors, role models, and leaders in the FIRST community and give them a network for career-related support and personal growth. And I was like, I'm in. What do we do? And so basically what we're doing, since this was started in November, and since this was the first large community event that Sarah knew about and was like, Renee, you're already presenting on advocacy. This is perfect, to tie in. Throw this out as an action item. So basically, it's a grassroots movement. It is for FIRST alumni and mentors who are over the age of 18. And it's, there are other amazing groups like First Ladies and First Like a Girl and things like that. And I would consider them like, the Facebook or Twitter or Instagram version of, this female empowerment group and like kind of this ability to network. But what we see Flame as, so, first female leaders for alumni mentor empowerment, is really this opportunity for people to come together and be more like LinkedIn. So that's what it is. People are welcome to email me. They're being invited to the Facebook group. You can search for Flame. Again, you need to be over the age of 18, but we're going to start with a trivia night in January as a way to kind of start team building. And we're looking to start building up ambassadors around the world, in addition to building up advocates and allies, in our non-female identifying individuals too. So that's my action item pitch is, if you're a female identifying person in the First Robotics program as an alumni or mentor and over the age of 18, find this group and let's start changing the world together.
Well, thank you for your amazing conversation about advocacy and being someone who is, I don't even want to say it without like belittling that amazing message you put, but like being an advocate for what you believe in and for the people around you. Like, that's very inspiring. I just want to thank you for putting it so well.
Absolutely. And, I guess anytime you want to connect or put a presentation together, I'm one class away from my master's. But that's really what I've been focusing on for a couple of years. And so now that I'm almost done with that, I have a little bit more free time to like pay attention to, I don't know, is Chief Delphi still a thing? I'm not really sure. Like Chief Delphi, Facebook groups, I don't know, support, offer presentations like this, etc.
Okay, well, thank you. I think, however, that does conclude your time. It does look like you wrapped up perfectly. So, well, I guess again, I'll just say thank you.
Absolutely. Thank you so much. That was definitely intentional. I am trying to stop sharing. There we go. So we should be good to go. Have a wonderful rest of the 24 hours of STEM. I'm so excited to see some other sessions. I'm also going to put a plug in for the LGBTQ plus of first session. I'm going to help moderate that on the back end. So I'm very excited about that. So have a good rest of your event.
Well, to you as well. Okay, then. Well, I guess switching over to a newer note, we're going to go over to our other speaker. It's my pleasure to introduce our next group of speakers, William and Evan. William, can I just ask a quick question? Would it just be you joining us, or is Evan joining too?
It'll just be me today.
I'll just be you. So I guess instead, just Evan. Evan is a member of FRC 5024, and he'll be talking about the value of a team library.
All right.
So it looks like you were a programmer, so I'm pretty sure this library is going to be pretty extensive and pretty interesting. Will it not be?
Hopefully, yes. I'm here to talk about our library and the benefits. Is my screen sharing correctly?
It looks like you're all good to go.
All right, sounds good. So a little far up here. Sorry, I'll go back. All right, so I'm here to talk about our award-winning software behind 5024. So I'm going to start with a brief introduction. So my name is William Meadow. I'm currently on 5024 Raider Robotics. I've been doing robotics for 2 years, and I've been programming for 6. This year, I was promoted to the lead software developer. Obviously, didn't get as much as I wanted from this year out of developing and working with robotics, but still making the best of it. So I joined robotics my grade 11 year. I've enjoyed it so much, I really regret not joining earlier. Honestly, my favorite thing in all robotics is just the atmosphere of the competitions. It's just amazing. It's like nothing else. So my team is 5024. We're based in London, Ontario. This is our 7th year running an FRC. And if you ever been to a competition with us, you'd know us as the big yellow mass that's constantly screaming. You can see a picture of my team right there. There's about 70 of us last year, divided to 7 sub-teams. Our motto, do stuff, do it well, is very much suited to our team. where every single person on the team, everyone I know, constantly gives it their all to do the best in everything they can. Our team's history. So we've been in 4 world championships, 2 blue banners we've earned, one for chairman's. We've had 2 logos. We recently switched our logo to a new modern one. I know a lot of people on our team were sad to see it go, but I'm happy with it personally. We won 15 awards. The award we won the most of is a Engineering Inspiration Award, which we won 3. That is in large part due to our yearly Science Expo, where we have kids come in and we demonstrate scientific concepts. It's really cool to see how enthralled they are with the science. Sadly, we weren't able to run it this year due to COVID, but it's an amazing experience. So our 2020 season, we were lucky enough to be able to participate in Infinite Recharge. We were able to attend the Humber regional event, in which we played against some very skilled and impressive teams such as 1114 and 3683, which are Team Dave and Symbotics. We were able to go 11-1 in the play-in stage, which I was very happy about. We were able to place the first seed. The story of how we actually got there was pretty crazy. In the last match, we were tied for first effectively, where if we won that game, we got first seed. If we lost it, we came second seed. And so we go up to get the switch. We have to level the switch and we win. And our one robot's not able to do it. And so what we were not able to do it, but our robot wasn't able to get in there because an enemy alliance robot was blocking them. The judges reviewed it and we were able to come in first with that. And the experience was crazy. I've never heard people scream louder at a win. So it's pretty crazy. We ended up making it to the finals where we lost. As the first event I've ever been to, I thought it was pretty good, but yeah. So the goals for this presentation. Our goal for this presentation is to demonstrate the history of our library, the advantages of the library that you'll gain from having one, and the systems we've implemented to take full advantage of the library. So a brief disclaimer. Libraries are not for everyone. They take a lot of effort to set up, but they can definitely be worth it in the long run if you're able to properly set it up. I'd recommend you don't build a library if your developers are changing what they do year over year. So if you're constantly changing what language you're doing, you're constantly changing stuff at a fundamental level, I wouldn't recommend it. I'd recommend you have at least 2 years of experience kind of in robotics. I wouldn't recommend this as a first year thing because you should know the basics of robotics programming. And the WPI lib tool suite is already pretty good. So if you're comfortable where you are, it's not a must. You don't need to have a library, but it's very helpful. So that's just a brief disclaimer. So what is a library? That's probably the most important definition of this entire thing. A library is a collection of pre-built tools that can be used in other projects. So stuff like classes or variables, as well as method and functions can be brought over into other projects. So if you had like a function that did the Pythagorean theorem from one project and you kind of stored that and then brought over to another project, that could technically be a library at like the most basic level. So lib5k's history. It started as an off season. It actually first started when we were on a bus back from a competition. So it kind of have a very humble beginning. The name lib5k comes from a combination of the word library, which is the lib part, and 5k, which is part of our team name, and also a chant our team does, where we go 5k and then the rest of the team yells 2-4. Anyone who has been in competition with us would know about that chant. So we started with very simple tools like stuff for outputting data, like logging information by outputting it, and simple math tools. So far, we've had 803 commits on the main file. A commit is effectively just when you change code, you add, you subtract, you change it in any way. That's a commit. We're constantly upgrading and improving it. So it's never the same. Like if you look at it one day and come back next week, it's not completely different, but it's always new stuff being added. We've also won 2 awards based on work that we have done with it. I'll talk about that later on in the presentation though. So the advantages of a unified team library. So minimizing the boilerplate. First of all, a boilerplate is a code that's repeated in multiple places with little or no variation. Something like in the subsystems in normal robot programming, to have a subsystem, it has to be a subclass of subsystem base. And it also has to have a periodic loop. So that'd be like the most basic example of a boilerplate. An obvious downside of this boilerplate code is that every time it needs to be rewritten for every instance where it's needed. So if you had 10 subsystems, you have to rewrite it 10 times, which kind of gets arduous after a point. So right here we have an example of a boilerplate for drivetrain code. The problem with drivetrain code is it's very easy to mess up, and it can be over, like, just have the basic functionality, it can be over 200 lines. So in this image here, this part of our library where it has we built a specific thing to reduce this called dual PID tank drivetrain, where you just add configurations and add the motors to it, and it automatically sets up the basics of the drivetrain for you, so you have to write less code. Another advantage of having a minimized boilerplate is you can it kind of combines it into smaller sections, so you can it's easier to integrate new software. So it's easier to test. Like, we integrate tests and we integrate simulations with some of our stuff. So in the bottom right image here, you can see a test that we integrated to all our auto paths. So in every single auto path, it'll run this test here, and you can see this is like the inputted path, and this is the actual path it would run. So we can do that, and we can get a better understanding of how our code actually works. So how we've used this, in 2019-2020 season, we began using a state machine system. State machines determine what the robot will do based on the states that it's in. So right here we have a diagram for what was I believe this was our cell superstructure. So cell superstructure handled the inputting, outputting of data. So it would rest in idle state, and when we got a inputs from a driver to switch to a shooting state, it would perform all the actions automatically and sit in shooting state until it's finished shooting, where it'd go back to idle. So it's a good way of organizing that. So we'd have 20, it would be for every subsystem where you'd want to implement it, it's 20 plus lines. So if you're looking at a subsystem and you had 10 subsystems, that's 200 lines just of repeated code. That's the very little variation. So what we did is we made a subsystem thing that's all integrated together, and I'll talk about it later, but it basically shortens this into 5 lines of code per document, which obviously a fourth of what it used to be, which is really good. We also added easier use of logging tools. So effectively, the logging tools are combined together. So the logging codes it's like combined into one. So you can just insert simple logging functions instead of having to rewrite the log stuff over and over. So if you want to write to USB, it's very difficult to do if you're to do it in every single thing. However, when we combine it together, you can just talk to one thing that handles all of it, and it kind of streamlines it all into a simpler way of doing it. So the advantage of that is obviously at competition, we can debug a lot faster. I know at one of our comps, we had the robot in the middle of the match. We couldn't, it just died. So we read the logs to see if it was an issue with programming or networking or just power, and we were able to quickly determine that it was not a problem with code, and we could look elsewhere. So that saved us tons of time when we were in the pits trying to fix the robot in a 3-match time zone. So it also allows you to thoroughly test code. So testing is an important part of coding that new programmers and old programmers alike both forget to do often. So what we have is you can build in unit testing. So unit testing is basically when you test code in units. So it can be ran automatically. So this here is an example of a test where we test the file management system. So it creates a file, writes to the file, and then it checks to make sure the file is written to correctly. So that would automatically run here. So if there's any problems, it automatically, as the code's built, it'll automatically tell us if there's any problems, which improves the safety of our code. So obviously, when you know code will work, it takes less time to debug. It also takes less time to write. So how this has impacted us. This is one of my favorite stories in all of robotics, or my experience anyways. So we went to an semifinals, and we had problems with our autonomous, where one of our teams in our alliance and our autopath kind of would have hit each other. So we had to quickly develop a new autopath. So we were only able to get 14 points out of the autopath that we were doing normally. So we had between quarterfinals and semifinals, we had to develop this new path. So we were able to trust the tools we had so that we could write the code without actually running on the real robot, which we couldn't really have time to do because it was in matches and then it was out of matches and it was just being fixed in that time. So anyways, what ended up happening is we got one shot to test it, and we didn't have access to the practice field. So we were sitting in the pits and we spun up the spinner, and one of my mentors was holding a cardboard sheet in front of the shooter to block it. And every single time a ball would thud against the cardboard, he looked terrified. It was very funny to look at. Anyways, this auto ended up being able to win us the semifinals and got us to the finals, which was really impressive for only being tested once. So as you can see there, we hit them over the line after we intake balls from them, which is pretty cool. I'll give you a second to look at that and just. So we feed the balls in and then we shoot them out. Anyways, so another advantage is abstraction. So we can hide basically complex tasks behind easier interfaces. So this allows a ton of benefits. One major one is being that it improves the speed in which developers can build and test code. For example, if a new programmer or even a more experienced programmer was asked to, if I told them to go and make something that did a complex math formula, say like the quadratic formula or something, I told them to implement it, they might mess it up. And that's just a simple one. They might mess it up. And I find math bugs are kind of the most difficult to fix, in my opinion. So this here is kind of an example of what a quadratic formula might look like. So that's kind of difficult to understand if you just look at that in a glance. Look at it in a glance, and you're trying to understand what this code does. It's just math numbers. It's just numbers on a screen, right? However, if you were to abstract it to make it look like methods instead, make it abstracted into just these methods here, it's a lot cleaner and you can understand what's going on a lot better. It also improves the safety of it if you're tinkering, because you can, if you want to change the weight of a number, so if a number is more important, you could set a parameter that does that safely so that there's no chance of you breaking it if you're trying to do it quickly. Like I said, it improves readability. So yeah, just tons of benefits, hides tasks, hides difficult stuff. And a lot of what the advantages of the library are based on abstraction. So abstracted code has impacted us. So obviously it's a lot easier to teach new members when they don't have to understand literally everything that's going on. Like when I first started programming for robotics, it was kind of difficult to kind of do code that was productive, like that actually had importance. Because for example, if you just wanted to set up a motor, you'd have to figure out how to properly configure it. You'd have to be able to set up an encoder. And in some cases, you have to add a PID controller on top of that. And at that point, I don't even know what PID means, which is pretty difficult. Pretty difficult to implement if you don't know what something means. So instead, what we do is in our libraries, we abstract the code so that we can make it easier for new programmers to write code. I'll show you a better example further on about how we set up our motors to work. So they're super simple, but it makes it a lot easier for new programmers to become productive, and productive programmers are a very good thing to have. It also removes the tedious and boring parts of writing code, because you get to go straight to the building and finding cool ways to do stuff part, which makes more fun. And that's the most important part, right? So awards and recognitions. Obviously, awards are important. They're a major part of FRC, and as a developer, it's your job to win the programming awards for your team. The primary awards given for programming are the Autonomous Award and the Innovation Control Award. One of the main problems for programmers is that not many judges have a background in programming, so they don't really understand what you're talking about. The good thing about libraries is they're extremely easy to explain. You saw earlier I explained what a library was in one slide very quickly. They're also very impressive. One thing about them is they have all your code, which is like all your best code usually, which is very impressive. Judges like seeing cool stuff like that. It also gives you a good point to jump off and talk about cool stuff you've done with your robot. Our experience with awards. So we've gotten 2 Innovation Control Awards. In 2019, we were able to tell judges how lib5k features were developed to be able to adjust the driver's errors in real time without using the sensors to tell position, because we didn't have many sensors on that robot. And in 2020, we continued to work with this technology, and we were able to set up a robot that could aim at the target using the limelight and move around depending on where it needed to be to shoot the best. So we were able to talk to judges about that, and we won a control award for the autonomous scoring last year. So our library features, I'll talk about some of ours that we have now. So at the moment, one of my favorite ones is the simulation. So it's really important for developers, and a lot of programmers in FRC will know this, that you never get time on the robot. So having the ability to simulate code is amazing. WPI already offers a simulator, but it's kind of difficult to set up motors and sensors to be able to utilize that. Having the ability to test code without needing a robot lets us keep up to pace with build team, because in prototyping phase, there's no actual robot and they're just swapping out parts and they're seeing what works. Being able to simulate it obviously lets us keep up with them so they can have code when they need to test new parts and all that. So all of our parts are automatically connected. All of our parts that we use, we've automatically set it up so they can work with the simulator, which is very useful. So we also have a unified hardware API. So for every part our team has used in the last 2 years, and some parts we haven't used actually, we have our own version of the code for it, or we have like our own version of it that powers it. And this implements abstracts methods that make setup the device simpler, use of the device simulator, like I was talking about earlier. The simulation is already integrated into them, so you can automatically simulate motors and sensors like that. And this makes it extremely easy to set up. Over here, you can see an image I have of 2 motors. You set up the one like this. It's one line per motor. So we have set up the one motor. We create one Talon completely configured and one Talon FX completely configured, which before it takes significantly more lines. I'll see the next slide, I believe. So yeah, our hardware implementation. So basically in the green wrap border here, you can see what it takes to set up a WPI Talon. So to set up WPI Talon, you need to first just gotta make it. You gotta construct it. So you do this, and you gotta configure it. So you gotta config, and you gotta figure out if you want safety on. You disable the safety, and then you set it to neutral coast mode, and then you invert the motor if you want it, and then you stop the motor. So it's very easy to mess that up if you're new. You might forget to set the neutral mode. You might forget to turn the safety off. You might forget any of those things. Obviously, kind of problematic if you want to set it up properly. I know in the past I messed it up as well. So it also looks ugly. So you gotta see all this when you can just, in our yellow, this is our lib5k version, where it's just like I showed you in the other example. It's just one line to set it up and it's completely configured. Now, if you wanted to change that, that kind of becomes a problem. But our solution to that is the ability to configure motors. So more experienced developers would want to do this. So what we allow is you can have for each manufacturer, there's a configuration class which stores all the data based on what can be configured on the motor. So if we want a motor that was set to go forward, you can pass in a configuration that has backwards to false. So this is a single one of our configs here, and you can see you can set current limit, you can set the brake, you can set the factory default if you want to do that. But other than that, it's all automatic. It would all be automatically done. So the way we do this is we do this through a factory design pattern. So ours is kind of a modified version of a factory design pattern. What it does is it allows you to create motors that have unknown configurations, or like it can make motors when you don't know the configuration yet. So what it does is it takes in the type of motor configuration that you want, configures it when it's creating it for you, and then automatically just returns the pre-configured motor. So you just pass it in the blueprint, it manufactures it like a factory, and then it builds it. And the blueprint in that analogy is obviously the configuration file. Another great thing about the configs is that if you want to switch a motor, if you have configs how you want them and you want to add them to another motor, you just have to copy the config and put it in the other motor, which is fairly useful if you're switching out between parts and doing other stuff like that. So integrated state machine. Like I talked about earlier, we had the state machine, which a big problem with the state machine is that it takes up 20 plus lines per file, which obviously isn't good. It makes the code less readable. So what we did is we created a state machine that is that reduces the size of that significantly. So you can see right here we have an example of what ours looks like. I have a better example in the next slide, but it also through abstraction allows for automatically logging files or logging data about it. So the developer doesn't have to worry about setting it up to properly log out the data. So that allows debugging to be easier and just improves the understanding that we can have of our code. So how our system works. So in the green, the state machine, this is what a normal state machine. This is directly from our code this year that handles the ball superstructure. So this handles the intake, the shooter, and the way we get it there. Anyways, so what it does is it would go through, it'd figure out what state we want, and then we decide what to enact from there. And we have to do logic up here that we could mess up when we were first writing this to see if the state, if we want a new state, if it's a new state or not. But over here, we reduce this significantly. This does the exact same thing as this, and in significantly less lines of code, and it automatically logs a state. So here we set a default state to idle, and then we can figure out what we want to do. We add these states, and it can figure out what it wants to do internally, and figure out if a new state internally as well. So our logging system. This is one of my favorite parts of our library. The logging system basically allows us to see inside the robot. It easily allows us to output data. So the data that can be sent out to driver station. It could be sent out to shuffleboard, or in our case, we have set it up so you can write to a USB connected to the RoboRio. Log data is extremely important when you're prototyping and debugging. Of all the things in our library, this has stayed the most consistent over the years. It's had minor changes, but it's been there the entire time. So the information can be logged. So effectively, we can log the time. So over here, it logs the time relative to how long the robot's been running. So if the robot's been running 2.2 seconds, we can see that it's been running 2.2 seconds. You can see here. So this here is us I think we're just powering up the robot's drivetrain on this. I haven't read through it, but I think that's what it's doing. We can log where it's happening, so we can read where in the code is actually happening here. So we can read that it's save log and generate time method in path generation path. So it's generating a path. We can also log the level of importance. So I'm not sure. Yeah, it is in here. Sorry. So we can log the certain different levels of importance. So if it's something that is extremely important, like a motor's not working properly, we can log it with a warning, like a warning flag, so that it's more prominent for us to see. We can log messages as well. So if we want to, right here's a message. So if we wanted to say like robot is moving too fast, we can output it to say robot's moving too fast, which is fairly useful for debugging the code. We can also do real-time graphing with this. So this year we have a shooter that works via flywheel. So when it spins up, we have a PID controller, and a PID controller controls how something accelerates and decelerates, and needs to be tuned so it properly spins up. So what we did is we tried to tune it, but the problem with that is it's going so fast you can't tell if it's speeding up or speeding down properly. So what we did is we have the data be output through the logger, and then we can read that data, and in real time we can build a graph of what the speed of the flywheel is. So this allowed us to tune the flywheel extremely effectively, and it allowed us to finish that way faster than we would have been able to otherwise. So thanks for watching. That is my presentation. I think we have questions now, or?
I don't think anything that's recently come up in the chat. Oh, let me just turn my camera back on. Sorry about that. I don't think recently we've had anything pop up in the chat, but definitely I'd like to just ask you a few questions or
Of
so.
course.
Um, so basically, I just want to give a little bit of a heads up. I myself was not the biggest technical person. I was more on the non-tech side of things. So hopefully, I
Yeah,
don't
that's fair
say
enough.
anything that's against what is norm. So I'll try and give my opinion. Um, I definitely like to ask. I have like 3 questions saved. First, I just like to ask, how long did it take you to build this library? Because I know you're only in the team for 2 years, but it seems like you grew alongside the library.
Yeah, so I've only seen like the half of it. The library itself is kind of interesting to say when it actually started because it's evolved a lot. Like the library as it is now has only existed for 6 months. The library that has existed like all along has existed, like the idea of the library has existed for 3-4 years. We've constantly upgraded it, so we're kind of in a state now where it's more modern, it's more sort of what it would be like in a real life sort of library. Like you can actually import it instead of how we did it last year where you could only like you had to just drag the files in and have them sitting in the file with you that you could easily reference to.
That was pretty interesting. I guess another question I could just ask would be, what do you think the hardest part of like making this library and using it is?
The hardest part, it's definitely planning it out because there's a lot of design choices that you make that will end up haunting you a while later. I know that a lot of the problems we faced is with having how the hardware works and how the simulation works together, because I know that obviously the hardware is different between manufacturers, so you have to have a way of getting it to work together from all the different manufacturers into one unified sort of thing. And that's why we have the factory with the config sort of full way of doing it. And then we have a lot of this is more technical, but interfaces where you can just give a class sort of required methods like start, stop, set speed sort of thing, so that we know what's in that, and that kind of has solved the problem of kind of hardware being different from each other. That's kind of my answer to that question. Yeah.
And I know you kind of hinted a little bit at like a situation where like you had a little bit of a misstep, but you overcame it when you were at the event and you had to like fix your auto. So I just like to ask, well, like I know like we all hear about the stories about like a situation you faced and it's like scary, but you overcome it. Can I hear just like a few more ideas about or like events or times or like there was a scary event or just like one of the most memorable events that comes with that situation of like failure but overcoming it?
I've only ever been to one competition, but certainly one of my favorite moments was like I was talking about with the logger, where our robot broke, like it just broke completely, and we had no idea why it broke. Like I said, we looked at the logs and we couldn't figure out what it was code wise. We ended up figuring some rail was broken on the thing. Another really interesting, one of my favorite ones as well was we got to the thing on the first day of the event, and we do our first test match. And I was the one working on the autonomous, and our robot goes out. I'm sitting there. I'm like, I really hope this works well. And the robot goes. It starts to turn towards a target, and it just keeps doing 360s in a circle. Um, and anyways, we get the robot. I'm like, why did it do that? Because there's no reason. We thought originally we tuned something wrong. It wasn't that. Turns out our gyroscope died. I think it was the gyroscope died or the Rio connection to it died. I can't recall which it was. But anyways, it took us so long to figure that out, and we had like probably 5 minutes to fix it. What we ended up doing is we ended up on the fly programming a new gyroscope to be used instead. And this one, before we were using the Navex, and obviously the Navex is a lot more versatile, but we started using the I think it's called the ADP something 450. We started using that gyroscope. It's only a one-dimensional gyroscope, but I've liked it a lot more now, actually. So I guess that was kind of a good thing that came out of that. That was one of my personal favorite experience.
Yeah, I know like from a few competitions that I've been in, just seeing some like the coding mishaps, Like I know one year our intake accidentally just like shot up and it went through one of the platforms, and like it was one of the most funny times because we're all in the crowd and all of a sudden like our intake shot up and it hit one of the pieces on the field, and we're all just like shocked, and then it was just like so scary just seeing it, but like just like overcoming it, and it's just like it's so amazing to see like you programmers are just like on the field, you're there to fix every issue, and talking about a library where you just have like a bunch of like code saved over and just like you're prepared for every
Yeah,
situation. Like
that's one of the great advantages of it, where you have the code already if you need it. Another problem we had was we arrived at the event for inspection, and they tell us we're using a I think it was a window opener or for window lock, of automotive window lock, I think it was, to pull a pin that released our climber. And so the judge says it's an illegal part. So we realized this is like the most important part of our robot. Anyways, what ended up happening is we had to get rid of it. Another team lended us, I can't recall what team it was for the life of me. I think it might have been, I can't recall. They lended us a servo motor that we could use to pull the pin. So we had to go and we had to program in this new servo pin. So we already had the code and we just plugged it in, new servo pin, and it worked better than the lock opener that we had before. So it was pretty good experience doing that as well. That was another fun one.
yeah, that sounds very scary, of course, considering it was one of the most important pieces. But that's just such an interesting thing to hear how like you hear it in memes, improvise, adapt, overcome. Like that was you definitely had to get through it. It definitely seems like you did it. I guess I'll just give the chat like some minutes to like type up any questions and see if we got anything in the chat real quick. And I think if not, if up to you entirely, if you don't want to keep going over anything, we might just, oh, we got 2 questions from the chat. Sorry about that.
All right.
Did you want to say something? I thought I cut you off.
Oh, no, I'm good.
Okay. So from the chat, it looks like someone said, what has been the hardest to track down bug you've had in your first career?
Hard to track down bug. There was one bug that I still never found out the answer to, but it was something to do with the climber, where the climber, what it would do is it would shoot up, and then it was supposed to come down to a Hall effect sensor, and it was supposed to stop there, but it'd go down. We had 3 along the line, and it was supposed to stop at the first one, and that was like the halfway mark. It would stop there, and then if we got another input, it would go down to the final one. I never, it went, we deploy it, it would work fine. It would go down to the first one, and then it wouldn't go down to the second one for no reason. We tested it so much, we could not figure out any reason why. Someone just changed something and it started working. So that was probably the difficult bug. I don't even know what fixed it. So I'd say it's pretty difficult to solve.
Yeah, and I just like to apologize to the person who put that in chat. I just didn't get to it. That's my fault. And for another question that we got was, how did the process of creating this library impact your future plans? Followed up with, will this experience change how you tackle software in the future, both in and out of FIRST?
Sorry, what was the first half of that question?
We can just take it in parts for now. There's just so much to that. How did this process of creating this library impact your future plans?
I think, like I said at the beginning, I've been programming for 6 or so years, but I started really doing it when I got into FIRST. I think in terms of it, I actually get to see practical uses for like all these cool tools that exist. Like, I've learned how we actually do, like how you actually package software together and make it so it's able to actually go out and deploy to different things, like deploy to actually other people could just put in their code like that. Another part that I thought was kind of cool was how we set up our documentation, where like this is the real world sort of support you have to have for it, where you can document code and you're able to explain it to people and other people actually are using it. So it needs to be readable. Because I know when I'm programming on my own, it's very often I just go off on sort of programming tangents where it's just incomprehensible code, but it works. So I think that's a main thing, where other people are actually looking at your code. So.
And perfect. And the second part to that question being, Will this experience change how you tackle software in the future, both in and out of first?
Um, I think, yeah, definitely. Like I've learned so much about how software should be designed. Like it should be designed where it can work in the future and stuff can be changed. Like it has to have expandability and scalability, which in the real world are two very big things. Like there's a lot of infrastructure and different types of software in place to be able to scale stuff. And I've learned a lot about how you scale software while working with people. I think that's probably the biggest thing I'm gonna take with me when I leave.
That's nice. And looks like we actually have one more. Um, this question asks, how does your team manage communication of how the library works over years?
So far the library's been programmed by sort of one sort of generation, I guess, of people going through. So we haven't actually had to sort of hand the reins to an entirely new group of people. That's going to change next year when the entire group that originally started working on this graduates. One thing that we've been doing is we've been trying to document as much as possible. We have extensive pre-generated Java doc, which is documentation generated that's just automatically generated that tells you the outline of how code works. We've also been working on writing down sort of a guide of how it works. If anyone is interested in that, it's cs.5024.ca/lib5k. And we have all basically how everything works written down there. And as we're going through this year, we're still trying to document as much stuff as possible because a lot of our senior sort of programming people are graduating. So yeah, just document writing stuff down. That's what our key sort of thing for passing it on is.
Okay, so it actually looks like the chat is really going off now. So it looks like we're actually going to stick in this for a while. Another one of the questions in the chat says, can you explain how your team handles the handoff from mechanical to programming?
So mechanical programming, in the beginning of the year when we're still in the prototyping phase, we have our programmers go out and we try to keep them as much in the discussion as possible with build. So we try to talk to build, make sure they know if you're planning on doing this, we need A, B, and C sensor. We try to keep them in with knowledge of what we're kind of doing at a top level. Obviously, they don't need to understand the bottom level of how the code works and all that, but we try to make sure that when the codes, like when the mechanics of it are actually being built, we are part of it, and we know at all times what's about to go on, and we know and they know what we need for sensors.
Perfect. We still got two more questions to go, and probably a bunch more still coming in. Another question starts off stating, you mentioned that the lib5k library is useful for new programmers. How do you recommend introducing/teaching new programmers to FRC?
I've actually experienced this as I'm teaching teaching some new programmers for our team this year. One of the main problems I've had is obviously being remote. But what I think is the best thing to do is don't even start them. If they don't have a background in programming, don't even start them in FRC. FRC programming is, in my opinion, so much different than actually programming just by yourself. I usually start when I'm teaching, I usually start off by introducing just the core concepts of programming, variables, classes, methods, all that stuff. Then you slowly work your way in. One thing I kind of been doing is I have them build systems for me. So like I'll have them build I'll show them kind of what a drivetrain is supposed to do, and I'll have them build a drivetrain. One thing I'm planning on doing is I'm planning on making basically a folder, giving it to them, and then saying, build me a robot is what one of my plans is to do. I think teaching them by having them lead and you kind of there to support is the best way.
Perfect. And as of right now, I only have one last question to ask, hopefully with a bunch more coming in. But if not, no pressure on anyone. This question asks, do you accept pull requests from other teams that may use your libraries with extensions?
That depends. Obviously, if we think it's good code, we'll pull it. I mean, it's completely open source. Obviously, good code is something that will be accepted and it's obviously reviewed. But other than that, yeah, we accept all pull requests.
Perfect. And we just got another question in chat, so let's follow it up. How much of a difference does the logging make in debugging code between matches?
Honestly, it is amazing. Like I said, being able to tell what the robot's doing is a crazy insight because you don't have to remember what is going on with the robot or like what actually happened in the field. One things that I didn't talk about in the presentation is you can SSH into the robot where you can just connect right into it and you can read the files without even having to touch a USB. I personally didn't do too much work in the pits, but I know from what other people have told me that it's just a lifesaver being able to know what's going on. Like I said, yeah.
And with that, I guess I'll just give a few more seconds to let anyone wrap up some questions. But I think at the moment we've wrapped through most of the questions. So yeah, very interesting, especially from a pair of eyes that have never been in the programming field before. So very amazing to hear about libraries,
Yes.
especially how you said a bunch of like it works with other things like functions and use use a bunch of math and applications of other things.
Yeah.
Oh, and someone just made a comment saying that the logging looked neat. So
Oh, thank you. Whoever said that. All right.
okay. So I guess if it's all good with you, if you don't want to make any last.
I just like to
Oh.
say thanks to everyone who's helped me make this presentation. Shout out to Mr. Tiet for being a great mentor. I know you're leaving us a bit this year, but other than that, I think that's what I'd like to say. Thanks
Okay,
for
well,
watching.
actually, apologize to keep you for another few seconds, but I would be glad to say that we actually did get one last question. One more question.
Great.
It says, "What are you looking forward to when you get back on the field?"
When I get back out, unfortunately, I'm graduating this year. I kind of missed out on being able to go through the whole comp phase as I've only got to go to one, right? But I most look forward to seeing all like the new robot designs. I know I'm programming, but the mechanical side and the engineering side is one of my favorite things to look at. I just love the innovation people bring.
Well, yes, it's just full of the most amazing innovators that I've ever seen.
Like I went to an event. It's like I would never have thought of an idea to design it like that in a million years, but someone designed it and they did it, right? So
yeah. And also another question coming in. Thanks everyone for the questions. What advice would you give to other teams wanting to make a library?
Advice, I think I'd start with a plan. It's very important to set up a plan. I'd say get 3 or so features, and then make a plan on how you're gonna set those up and get those executed. And then basically that's just to get your foot in the water, so you know how you're supposed to design the library, how you kind of want to do it, and then kind of just continue expanding it on from there. And any cool ideas you think of, just start adding them.
Cool. And since I always, every time I say, let's give it a few more seconds to see if we get any more questions. I guess let's just give a few more seconds for the chat to just log in some more questions. But if that doesn't happen, then I guess I'll let you get back to giving a great shout out to a teacher that you, or a teacher and mentor that you seem to appreciate too.
Yeah.
If we don't get one more. So just give it like 10 seconds or so and we should be good.
All right.
But I'd just love to say that it was an amazing presentation, and
yes, thank you for having us.
Well, thank you for being available to join. So with that, I'd just like to say thank you for being part of our stream, which I just said, of course. But looks like that wraps up this presentation, and we'll be back at 8 p.m. for another stream. And in the meantime, we have some great videos that we'd love to share with you. So William, thank you for being here.
All right, thank you. Bye.
Have a great night. And to everyone else, we're queuing up the videos as we speak.
Hummus. But hands-on is just go into it. Instead of saying, oh, I know how to build this robot. I can say, I built this robot.
In First Tech Challenge, students are developing a broad range of skills.
Manufacturing, hardware, troubleshooting. But there's also a lot of things that you learn that you wouldn't necessarily think about. People skills.
Problem-solving skills, helping one another, helping other teams.
The program draws so many students that come in who just want to do the marketing, who just want to do fundraising.
You need to do fundraising because you need to buy kits and parts and everything you need for the year.
And that's a great thing that the kids learn very early on.
The model of FIRST has provided incredible opportunities for the students to interact with professionals.
Whenever I ask my mentors the question, they always flip the question around and ask, where would you find the answer to that question if I weren't here? They slowly built my confidence up so much more to a point where we weren't asking them questions, we were just going.
Each team has to compete at a local event, win awards at the local event, and then they're able to move on to the first championship.
You walk into the room and there's that smell. The smell of robots.
There's different languages, different culture. It's just the best thing ever.
I think it's incredibly important for youth to see careers in science and engineering as a possibility for them.
High school participants have access to over $80 million in scholarships from colleges, universities, and technical programs. First Tech Challenge is one of 4 engaging FIRST programs.
First in one word, wow.
Fun!
First is inspiration.
First is amazing.
First is hope.
FIRST Robotics Competition is the world's landmark robotics competition for students.
Challenge comes out every
FIRST Robotics Competition is the world's landmark robotics competition for students.
In school, you read about stuff, but in FIRST as a whole, you actually go and do it.
In the beginning of January, the challenge comes out every year. Under strict rules and limited time and resources, you have to design, build, program, and test a robot.
There's no blueprint. We get a few rules and guidelines to follow, and then it's up to those students to find something that works.
There's nothing better than just seeing your robot on the field playing for the first time. They're all there like, is it gonna work? Is it gonna work? And then when it works, it's the best feeling ever.
You have mentors that are actually in the field that can tell you, oh, this is why this works, and this is the science behind it. And you're like, oh, wow, that makes so much sense.
They do a great job, not just about STEM, but about life, how to go through college, how to go through, a tough, physics class.
At face value, FIRST Robotics Competition is a robot competition, but at the end of the day, it's so much more than that.
People ask me like, oh, you build robots? I says, no, we're really running a business and all the things that go along with that.
We deal with a lot of marketing, social media.
I've learned business sides of things,
problem solving, working in groups.
I'm learning how to communicate with people, how to reach out to local businesses.
So we kind of have robotics as the starting point, but we branch out to different areas and expand.
So the ultimate goal every year is always to get to the first championship.
The first championship is basically like the Olympic for robots.
There's hundreds of teams from all over the world there, and you get to see some of the best teams that exist.
It's very competitive, but you're friends with the people that you're going against. It's like a sport, but in its own way, it's better than a sport.
Being part of FIRST, it's really changed my life and how I think about myself, how I think about others.
Participating in FIRST actually taught me that I'm capable of doing anything that I set my mind to.
FIRST has really inspired me to give back in my old elementary school. I'm trying to help their robotics program that just started this year. I want those kids to have the opportunity to learn about STEM.
As a participant in the first program in high school, you get access to $80 million worth of scholarships.
There are scholarships for colleges, universities, as well as technical programs.
It also looks really good on the actual application to be on FIRST.
FIRST does a really great job trying to open programs to make sure that you could actually accomplish anything in STEM, no matter where you're from, your background, your language, or anything like that.
I really do consider myself part of the STEM community, and I couldn't be more prouder to say that.
FIRST Robotics Competition is one of 4 engaging FIRST programs that shows students unique challenges and helps them learn new engineering skills and real-world skills that'll help them in the future.
FIRST is the future.
FIRST is accomplishment.
FIRST is passion.
FIRST is inspiring.
FIRST is changing my story.
Makes the dream work. When we do it together, teamwork makes the dream work. 'Cause together we're better. Learning, playing, building, singing, coding, making friends, believing. Every boy and every girl, FIRST Lego League. Every boy and girl, we got a place for you somewhere on our team. Yeah, yeah. We are here to learn, compliments and memories, be a champion.
It's so fun and exciting. Everybody come join in. Future jobs we're designing. Let's begin.
Every day we're celebrating science and technology. Everybody wins in this community. Teamwork makes the dream work.
'Cause together we're better.
Learning, playing, building, singing, coding, making friends, believing. Every boy and every girl, FIRST Lego League. Grab your robot and dance now. Build a bot now, let's get to it. Grab your robot and dance now. Every boy and every girl, FIRST Lego League. Builders, designers, mistake makers, risk takers, innovators, educators, coders, thinkers, friends and tinkers. You can be anything, so just do it. An astronaut, a scientist, an engineer, archaeologist. See it, believe it, and we will build it. FIRST Lego League.
Hi, my name is Sarah Heimlich, and I've been involved with the FIRST family of programs since I was 10 years old. This program has literally changed my life. I started off as a very shy and quiet 10-year-old who would literally hide.
Okay, well, I'd just like to welcome
Student
But what would you
who's
see
interned at
if you
Google,
looked
and I'm a
closer?
member of the Australian Regional.
I apologize for that. That was a mishap on my behalf.
This is Morgantown, in north central West Virginia, the home of Mountaineer Area Robotics. Each year on the WVU campus, Mars designs and constructs a robot named Marvin. But building a robot is only a single step towards our goal, to foster change in our home, West Virginia. This mission, to inspire students in rural areas to pursue their creative and intellectual passions through programs like FIRST Robotics, seemed impossible just 10 years ago, but now we have a solution. We call this solution the Mars Plan. The first step in this plan is engaging communities around us through visibility. Using this engagement as a springboard, we inspire the creation of robotics programs utilizing experience and financial support gained by Mars over the past decade. We then focus on team sustainability by working closely with coaches and students, mentoring and supporting area teams. In addition to our assistance prior to competition, we ensure events are well run by volunteering as referees, event coordinators, and judges. This support keeps teams coming back, and in the past 10 years, we have more than quadrupled the number of FLL teams within West Virginia. This inherent sustainability to support this transfer of students, we are now expanding West Virginia's FTC, VEX Robotics, and FRC programs through efforts such as running the FTC State Championship and our FRC off-season event, West Virginia Robotics Extreme, the world's only 26-hour robotics endurance event. MARS expects to see tremendous growth within these programs in the coming years, mirroring our efforts with FLL, which we continue to expand. MARS is now working with the West Virginia School for the Deaf and Blind, West Virginia institutional programs, and within county school curriculum to grow the reach of the statewide robotics program to as many students as possible. Outside of our state, MARS also runs programs such as the MARS Tucker Team Help Desk, a program that allows other FRC teams to receive assistance in mechanical, electrical, and software areas, inside and outside of competitive spaces. MARS is now expanding this program to a national level, training other teams to run their own help desks across the country. For 10 years, MARS has strived to become a driving force for STEM education in West Virginia. The MARS plan is working, the state of West Virginia is changing, and we will never let it stop. We are part of a revolution. We are MARS.
Okay, and now that we're actually back this time, no longer a mishap, I just like to say welcome back to the stream. It's almost time to start, but I'd just like to say hello back to everyone so we get back into starting. I know recently I got a little bit of snow up where I am, so I'm definitely shivering. Not because of the anticipation of what comes next, because I know we do got something pretty interesting coming up on board too. But yeah. It's definitely this fiery desire to get into it that's just keeping me going. And looking as it is now 8 o'clock, I guess it's time to introduce our next speakers. So I guess with that, I will introduce Cameron and Joshua from Team 503. So yeah, welcome guys. And yeah, it looks like they'll be doing an interesting interesting presentation on simple 2D robotics simulation and applications, and it looks very interesting. So before we start, I'd just like to ask you guys how you doing and like how excited you are for this.
Well, thank you very much, Team 125, and we are doing great. We are very excited for the 24 Hours of STEM event. All the past streams have been going very well, and especially the challenge streams and the Mentors Without Borders, those all have very interesting subjects coming up, as I can see. And I'm really excited.
Yeah, sure. Shout out to our other streams, that they all been running and they're all going to keep running. So if you ever get interested, you can always just make sure to go check out those too. But for now, we're definitely going to heat up as Frog Force comes in to drop an amazing presentation. So I think with that, I'm going to hand it off to you two. So yeah.
All right. Well, thank you, Team 125. So in this presentation, we're going to be going over how you can set up 2D robot simulation in Java for your robot. And once again, this is just two-dimensional. So usually it will involve the rotational components from an aerial perspective. And we also show two applications that we've actually had over this past off-season that both involve the actual mechanical movements as well as things that we get from sensor input. Just to give a little bit about ourselves, my name is Joshua. I am the programming co-lead from FRC Team 503.
And my name is Cameron. I'm a programmer as well on Team 503.
All right, so first we're going to start off by laying down all the contents that we're going to be going over in this presentation. So first we're going to basically introduce the core simulation concept that and the goals we're trying to achieve through this project. Then we'll go over kind of like the requisite knowledge that you should try to have like beforehand, whether like that includes having prior Java knowledge or simple math knowledge. Then we'll start off by showing how you can draw the graphics on the JPanel and JFrame components, how to animate those graphics, how to determine the motor's motions or other motions that we'll also have to calculate. And then Then we'll go straight into our practical applications. So the first one being our test with probably the most complicated ensemble you have, which is turret and swerve. And then we'll take it even further by showing you how that assembly works with a full real-time sensor input.
All right, and one second, sorry. We're gonna start off, give a little background as to why this was something that we wanted to do. So obviously current restrictions are forcing us all to have less time with the robot. Most of the time we can't even get into the shop. So this brings kind of a issue, is that we want people to be able to test and write robot code without having access to it. And this could also be useful in the future for helping teach basic robot code to new members without having to give them the whole robot. So some of our goals for this was we wanted to have opportunity to simulate systems on the robot accurately. We wanted to have a visual representation of the robot along with a mathematical simulation, and have it so we could accurately be able to see what's going on instead of just reading print statements to see what was being printed out. And we wanted to have code that was able to easily transfer into actual robot code, because when transitioning from the off season to the build season, quick translation time means that we'll have more time to actually work with the robot. So some of the stuff you should probably have some background on if you're going to be going into this topic is you should have some prior knowledge of Java. You should be able to kind of familiarize yourself with the code without having to like research basic Java concepts. You should kind of understand how threads run and how you track time from iteration to iteration. You should have a basic background on Swing and JavaFX. And we have to cover graphics and transformations of those graphics, along with how those are contained within JFrames and JPanels. You also need to have a little bit of a math background. You should at least be familiar with geometry and basic 2D shapes and transformations of them. A little knowledge of trigonometry is helpful, but it's not completely necessary for the basics. And you should have a general idea of how your robot mechanisms functions, because how are you going to simulate them if you don't know how they work?
All right, so now to get into the first step of drawing the configuration, and this includes pretty much your entire layout, the environment your robot's in, as well as the robot and the components of the robot itself that you want to highlight. So this is where we start to get into drawing using Graphics 2D in Java AWT onto a JPanel. So the first part is simply to have a container. So this includes having a JPanel and a JFrame. And then there are certain settings that need to go along with that, which include being full screen and undecorated so that you don't get the border in the way, and then the JFrame close operation. So I'll be showing those three lines now. So if we go over to this line over here, as you can see, we have first defined our class to extend a JFrame. So the JFrame is the parent class. So every method that we invoke inside this class is actually extended from JFrame because the class is a JFrame itself. Within the JFrame, we instantiate a JPanel, and inside that JPanel is where we actually override the methods for add, notify, and paint component. We figured that this method was a lot easier than having to create a separate nested class and have that extended JPanel and then override the methods in there, because it's way simpler to do it like this. We'll get back to add, notify later. But once you've basically created these two methods and you've overrided them, you have the paint component, which will draw all the graphics, which we'll also get into a second. But once all those graphics have been drawn, to actually make the panel visible, you have to call the add method. So you add the panel, And once again, because we're not specifying anything before add here, this will make it so that we're adding the panel to the J-frame. Now, once we've added it to the J-frame, we just have these few settings that I already described a little bit earlier. Because we want this to be a completely full screen application, we have to make it so that really just try to like memorize these certain statements that go along with the J-frame. So we set it to the J-frame maximize both state. This is just a enumerator. And then set undecorated to true. This will make it so that when we, like, for example, this window over here, right, this my IntelliJ, as you can see, I have this whole toolkit above over here, and the X and the restore down and the minimize and my taskbar over here. Like, all those won't be visible if you set undecorated to true, so it'll be a true full screen. And then set default close operation will make it such that you are able to just like whenever you Alt F4 or you just close out of the program, it will automatically stop it for you. So you don't have any ongoing threads, or usually you just don't want that to be the case where when you close the application, there's still something running in the background. So those are those 3 lines. And then of course, to actually make the frame visible, we over here in our main method, we just add the event queue, and then we make the frame visible by just instantiating ourselves and then setting to true. Okay, so now for the actual graphics, so drawing, we're first going to start off with the base level of things, which is of course the background. So the background is essentially the first layer. So to do that, we have to use something called image.io. And I'll show you where that is in the code right now. So over here, once again, all the graphics occurs under the paint component method. So of course, we have to override the paint component method from JPanel, and that has a parameter of a graphics object. However, in order to have all the variability that we want and good quality, we actually need to cast this to a graphics 2D object and create an alias out of it. So, so like usual for any child class or parent class, you have to call the super paint component. But then once you've done that, you can create an alias graphics 2D object and then cast the original graphics to a graphics 2D. Now, once you've done that, you're ready to do the next steps, which include drawing the image. So all these happen through graphics 2D. So we do g2.drawImage, and then we have this image.io class that just basically contains a bunch of static methods that allow us to easily do like image.io operations. And the one parameter that we pass through for this is a file object, which contains our file path. So then this is obviously how you like write the file path. Because as you can see here, this is my, my main directory, my project directory. Because the field JPEG file is within the project directory itself, as you can see over here, I don't actually need to specify any path beforehand, and I highly suggest doing it this way, especially if you're collaborating with your teammates, because if you have your like image located somewhere else, like on your desktop, then obviously it's not going to have the same path going from PC to PC. But if you keep it within the root directory of the project itself, you'll be able to access it directly without having any path before it. Coordinates 0, 0, observer null. And of course, the reason this is wrapped in a try catch statement is because it is an IO class. So it could always throw an IO exception if like if the file doesn't exist or if it's not able to render the file as an image. Okay. So now the next thing over here is a rendering hint, which basically allows our graphics to appear the way that we want them to. And the single one that we really want here is the anti-aliasing setting. Anti-aliasing basically makes it so that if there are any jagged lines that resolve from, like, how pixels are usually in an array of rectangles, if there are some that aren't just direct horizontal lines or vertical lines, they're like, if they are like diagonals or curves, anything like that, then you want those pixels to come out as clear as possible. So anti-aliasing basically takes care of that for us by eliminating those jagged edges. So you simply have to put this one line in the code that makes it so all the graphics components that we do after this point follow this rendering hint. So make sure you remember this line. At the end, we'll actually also show you our code release. So you don't have to perfectly remember it. A lot of it's like you're able to easily find it online. Like if you search up like what rendering hints do I need for anti-aliasing, you'll find this bit of code. But we also have a public release on our GitHub repo that we'll show in the last slide. So we'll get into that next. Now, the next thing is brush type. So brush type allows us to specify how the drawings come out on the window. So this includes color and thickness. So color is rather simple. You have g2.setColor, and then you specify in these parentheses what color you want it to be. Or you can also, there are two ways that you can specify the color. You can call the color class and then call the static, like the final colors inside them, which have some preset RGB values. Or if you want like a custom color that you've determined yourself, then you can go ahead and do that as well by doing new color. And then there are 3 parameters which are RGB consecutively. So like, because 255 is the max, will give me max RGB, which should be white. If you're using a good IDE, you should have like a little color picker next to here that will preview the color for you. And you can also like play around with it and dynamically like update the colors for what you want them to be based on what you're seeing, so that you don't have to just go around guessing numbers. So it's pretty intuitive. I can go ahead and set this back to its normal state, which was color.red. Right, so that's color. The next thing is your brush thickness. So the way you do that is you have to set the stroke of the graphics class. So you do g2.setStroke. Now this can also be used if you want to change the pattern of the stroke. So like basic stroke isn't the only option. There are other strokes like dashed or like dotted, which are kind of the same thing. But honestly, we're just trying to use this like a continuous smooth stroke here. So we're just going to use a basic stroke. And the main reason that we're setting the stroke here is so that we can change the thickness or the width. So here's the parameter for that. Is just within the basic stroke constructor. And we just set it to 2. And I believe the default up here is either 3 or 4. So when we're drawing like the robot's rectangle and all these other things, it's actually using a thickness of 3. And then later on, we want to transition to a thicker or a thinner stroke type so that we can show the turret's shape more intricately. Okay, so next over here we have our shapes. So of course, here's where a little bit of like, I wouldn't even say like geometry, but just knowing how numbers work over symmetry, like just shapes over coordinates, is really helpful if you're able to figure that sort of stuff out quickly and like efficiently, because this is some stuff that requires a lot of guessing the first time you're doing it, like until you get it to look like something that's in the right scale or something that you like visually. So there are 2 different functions. There's draw and fill. So those are, it's pretty self-explanatory. Like imagine you're on like Microsoft Paint, right? And you pull out the paintbrush, and if you just drag the mouse around while holding the mouse button down, that's essentially what draw does. So like when I'm saying draw a line here or draw a polygon, it's just drawing an outline of that shape. Now, when you do fill on the contrary, if you do fill over or fill polygon, these are all options. Not just because I'm using draw here doesn't mean that fill polygon doesn't exist. If I'm using fill in those areas, not only will it do the outline, but it will also get like the paint bucket and fill it in for you using whatever color that you have currently selected in graphics. Or you can do both. You can say, oh, I want my outline to be this color. So I first draw the outline and then I change the color and then I do the fill. So then it will do the fill for me. Okay, so now simply how these coordinates work. So I'll actually run the code here just to quickly show what this looks like basically. So here's the rectangle that I've made in black color, and then the turret, which is this green little shape over here. So the way that these coordinates work in terms of locations is that like over here on the top left, I don't know if you can see my mouse cursor, but at the very top left of the screen here is where x0, y0 is located. Now the direction of the axis works that this direction is positive x. So to the right is positive x, and downwards is positive y. So make sure you get that one clear, because I know in your math class you're usually familiar with your bottom left being 0, 0, the origin, and then up being positive and right being positive. But the way it works is that this is 0, 0, and all the way to the right over here, this is basically, it's defined by whatever your screen resolution is. And then all the way down here is defined by your screen resolution height. Just know that positive y is downwards. That's honestly the main takeaway of what I'm trying to say here. Now, the way I drew the polygon and the rectangle, if you're wondering, this is where it's really important to like record your numbers in a way such that like you know which number means what. So here, the parameters for the rectangles are x coordinate, y coordinate, then width, then height. So if I go ahead and run this again, x coordinate, y coordinate, those are the coordinates for the top left of this rectangle over here. And I know that might be hard to understand because you would assume that it would be the center, but it's actually for the top left. Now it might be asking, what if I had like a circle? Now, there's no really top left of the circle. I mean, there technically is, but would that be the top left? Because that's not really the top left of the full shape. Well, the way that it works is that if you have like a circle here per se, then you would have, then basically the program visualizes a square around that circle like this. The circle travels as one unit of a square. And the top left corner of that square, that's the coordinate that circle is going to go to. So now you just need to make sure that you're following symmetry while you're making all these shapes. So the polygon, the way it works is that you have an X interarray and then a Y interarray, and then it just assigns each respective X to a Y and X to a Y, and it connects all those points together in the order in which you have listed them. And then you just go ahead and draw the polygon out. And then the rectangle, we did like a little fancy 3D rectangle here. It's honestly not necessary, but you can go ahead and do that if you want to give it a little bit of a beveled look. Then the last step after you've done all your drawings is this last line here, which is toolkit.getDefaultToolkit.sync. That this basically just syncs the graphics with your display. So after doing all of this, you need to make sure that you call this method. I believe I don't know the technical reasoning for this, but the main reason that people usually invoke this method is to improve the frame rate of the graphics or the way that it renders. So this is just once again another thing that improves quality. And as you know, simulations, you always want to maximize the quality for that. Okay. So next we're going to get into animating these graphics. So to start with that, we need to go on with how we create our thread. So the first method that I kind of just went over was the add notify. So the add notify just runs as soon as the JPanel is initialized. So you can think of this as just a one-time thing. It will just run sequentially down once the panel is initialized, and then until we get to this while loop over here. Now this while loop will obviously get looped because it's a loop. So, but everything before then is just run once. Now to show you what this add notify method does here, what we specified differently in the add notify is we first have the sleep, which is wrapped into try catch once again because of interrupted exceptions. You always have to do that whenever you're calling thread.sleep. The reason we call sleep here is sometimes, let's say I have no sleep, right? And I run the code and I see something happen, but I barely get to see it in time because sometimes the window takes a little while to render, but the program has already started rendering. The program has already started running before the window has rendered. So you need to make sure that you add this delay here sometimes so that you can see when that actual motion starts happening, especially if it's something that happens right in the beginning of the program. So you can add a delay here as an option. Okay, now we get into our thread time management. So here's how we construct the thread. First, as you can see, we create a thread called animator and we instantiate it. And then because we're only trying to override the run method, we can simplify that into just a lambda expression. And then once we open into this thread here, we define our time variables as longs because, as you know, the times are all as those long integers. And then we're ready to enter the loop. So once we're in the while loop, right, we have our initial time, right before we started the while loop, stored in before time. But once we've entered this, we need to monitor our time diff, which is basically just our current time minus the time recorded in the last iteration. So before time initially, right, is just defined as the last value recorded of time before we started this while loop. But at the end of every iteration of this loop, we'll reset before time to whatever the current time is so that it's ready to be used again for the next loop to determine the diff time, which is basically how much time has passed between the last iteration of the loop and the current iteration of the loop. So you can call it uptime, diff time, same thing. The reason we want this diff time is we need to see how off we are from the exact period of the thread that we want. So the period is basically how much delay we have, how much time interval there is between every iteration of the loop. It's something that we actually try to set in the code. Usually we only want this to be 20 or 50, but over here to exaggerate how good the FPS is, set it to 5. All right, so then Oops, lost myself here. So then once again, once you've recorded the time diff, you need to subtract that from your delay. So let's say my loop has told my loop tells me that I have passed 20 milliseconds in this loop, but I want to have a delay of 50 milliseconds. So then this 50 minus 20 tells me that, hey, I have to sleep for 30 more milliseconds if I want to have a consistent uptime in my loop. So this is how you make sure that you're consistently getting the same time allotted to each iteration of the loop. If the sleep is less than 0, that means actually that your code did not run in enough, it took way too long to run. It took longer than the time that you wanted it to, right? That's what will result in sleep being negative. So if that's the case, then so as to not create an error, we just set sleep to 0 and then we don't sleep at all. But just know that that means that you're running behind in the code, or your code is running behind. And I don't know if I specified this, but the way that you get time is in system.currentTime millis. This is like elapsed time from some time, like a bunch of years ago. But this is going to be in milliseconds. And just understand that if we're going to use it in the context of time and you want to actually measure the exact seconds that have passed, you'll have to divide it by 1000 so that you get it in seconds. Then lastly, once we've defined our entire thread here, we've defined what it does. The last step of the add notify method is to run animator.start. So we'll just start the thread. Okay, now the last two very important methods are cycle and repaint. Now this actually updates our where our subsystems are virtually with what we're displaying. So this basically is all. I'll go over repaint first. So the paint component method, remember, this is the part where we put all of our drawings. This is where all of our drawings take place. But this is all just one instance captured of it, right? This will run once we initialize the JPanel. However, when we start rotating our turret, we need to make sure that we keep updating this, or rotating anything that changes. We need to make sure that we're constantly updating or calling this method once again so that it refreshes with the new variable so that it prints a new image, and it basically gives the illusion like we're animating it, like we're moving it, or it gives the illusion like we're moving it, which is the definition of animation. So that's repaint, and I'll show you where we call that here. You call it in the while loop, cycle and repaint, as you can see. Then I'll go over to cycle here. Cycle is a method that we actually create. And that is to simply update these variables that contain our robot's position and rotation attributes. So simply what that requires us to do is to run the simulate method from our subsystem, which we'll also get into later how we simulate that. And then actually get the positions, the angle of the turret, the angle of the robot, and then the position of the robot. So now if we go ahead and the next slide, I'll show you guys how to actually transform the images, because you'll need to do that in order to actually move the drawings according to wherever your robot's components are virtually. So the way you do this is simply by doing g2.translate, and you translate it a certain x coordinate and a certain y coordinate. Now, in our simulator, remember, these are the variables that we're updating from our simulated subsystem. From that simulated subsystem, the way that we interpret our x and y coordinates is the way that you normally learn in your math class. So your x is positive when you travel to the right, and your y is positive when you travel upwards. Now, because it's the reverse for y, we just need to negate it here. Then for rotate, right, we have a robot heading. We rotate around a certain point. So this is once again where it's really important that you record the points of your polygons, your shapes, so you understand where the center of each of those shapes are, because the centers are not the same as the coordinates that you have specified as the location. So we're rotating the robot around this point. And it'll rotate once again. These are all in, or I haven't mentioned this before, so these are all in radians. So make sure that whatever information that you get from a subsystem, if it's in degrees, you need to make sure you use math.toRadians to convert it to radians. Then so that's simply put translate and rotate. Now, why am I doing it in this way? Why am I rotating it just around this one point? The reason is because this translate honestly does all the work for me. That's why you want to look for the places, as many places as possible, to not have to do a necessary trigonometry, because that can overcomplicate your code when there's already stuff that does it for you, or just moves it around quite literally. So the reason we call the translate before the rotate is that this point as well, the point around which the robot rotates will rotate, will translate with this translate function. So that's why g2.translate and g2.rotate, they're all called from the graphics. You're rotating all the graphics. You're not just rotating one specific object around this point, but you're rotating everything that the graphics gives you after that point as well. So the reason that we call these are the first transformations that we do, the translation and rotate for the robot. The reason we call them before is because they translate and rotate all the graphics. And this is where you need to consider binding, like attachments or binding constraints. So for example, the turret is attached to the robot, but rotating the turret doesn't necessarily rotate the robot, but rotating the robot does always rotate the turret. So this is where you have to understand that you need to, wherever you rotate your turret needs to be a lot later in the code. So over here, for example, like near the very end. And sorry, if you guys don't have some like background knowledge on what some of these mechanisms are, like a turret is basically something that allows us to aim the shooter in a different direction along the robot heading. So later I'm going to animate this, you'll see this guy rotating around. And then our swerve drive just works in the way that we're allowed to translate and rotate on all directions of the field. So now to determine the motor's motion, I'm going to really try to gloss over this one. So this is where most of our research took place over the off season. This is where you actually calculate how the motor's moving depending on what power you're giving to it. And it's not as simple as you think, because you want to make it as physically relevant, as physically practical as possible. Like it can't be something that's that looks like it's artificial and not real. So the way we do that here is we found this equation for a simple motor online, and it just shows all these electrical constants and how they work together to determine your voltage. And then also we found a separate one that describes the relationship between voltage and acceleration. But what you need to understand from this is that our voltage just basically is the input that we assign to any of our motors on the robot. Whenever you say 0.5 power, negative 0.5 power, it's not actually the power in like watts or anything like that. That's just the term that they use to describe percentage of your bus voltage. Your bus voltage is usually going to be like 12 volts. So if you're giving like 0.5 power, then you're giving 6 volts. So now we need to figure out that relationship so that when we're calling our subsystem and we're trying to assign a power in those volts to it, that it knows how to figure out its acceleration in all of its kinematic variables. So how does it do that? This is first deriving acceleration. So we start at acceleration and then we move upwards. So acceleration is a simple equation here where we just take the load constant. So this is just like a fudge factor that you can compile from these. This just requires some playing around with when you're creating your first simulations, because they don't have to be your actual robots like constants from that. You could use that. It would be probably more relevant, but for the sake of like just testing like autonomous code and seeing how it performs, then you don't really need to do that. You can contain it all in one variable. We do that multiplied by your max velocity times t demand minus t omega. So this is just t omega is your turret's rotational velocity. T demand is the percentage power that we're assigning to the turret. So this is our input, and this is in a way our output. Like we'll do more with this output to actually get it in the way that we want it to be. But what this currently does is we take our percentage demand, we multiply it by our max velocity, and that's essentially our projected velocity. That's the velocity that we're estimating our velocity, our turret will go at. But you can set this constant for whatever you want it to be in your code. This is just like degrees per second. So what this code basically describes here is that the difference between the velocity that you are expected to go at and the velocity you're going at right now will determine how fast you accelerate. So the farther you are away from your target velocity, the faster you'll need to accelerate. But the closer you are to your max velocity, then the less you'll need to accelerate because you're pretty much already there. And so now to quickly describe how we take the acceleration calculations and make that our position. This simply requires this integration, and we know these kinematic relationships because velocity is just the integral of acceleration with respect to time, and position is the integral of velocity with respect to time. If you don't understand what that means, no worries, because it's calculus, but you do honestly just need to understand how that works in the code. So as long as you remember to like basically copy this and put it in your code for whatever mechanical components there are in your robot that you rotate, translate, or whatever, you need to make sure that you use an assignment operator to take the integral, and you need to take basically the derivative of this one and multiply it by dt to basically take an antiderivative of that out of it. So you have t alpha, which is the rotational acceleration, multiply it by dt and constantly increment it, you get your t omega. And then you do the same thing over here, t omega times dt, you get your t theta, which is your position or angle. Same thing over here for translation, right? We have x and y. These are called velocity and acceleration. Why? Because they're not rotational components. Alpha, this as a reminder, is acceleration. Omega is velocity when you're talking in the context of anything that's rotational. But over here, we have rotational omega once again. This is r omega, though. The reason this r omega is because this is your robot's heading, and this is your turret's angle. So we apply the same equation to all of them. So now I'll just give my first example here on how this works in our turret swerve sort of ensemble here. It's like the way that it works is we have 3 variables or 4 that are constantly managed. We have the turret's angle, we have the robot's x, the robot's y, and then the robot's angle. So to start off with the turret, we create a subsystem, and the simple way that we create inputs and outputs for it is a getter and setter. We actually don't have a getter in this case because we're not testing it on a real robot, but when you move on to a real robot, you'll want to have a getter just for diagnostic purposes to see what your code is sending. Set power is what allows us to actually create inputs into the subsystem. So there is where we'll have to put our motor kinematics formulas that I showed you on the previous slides. And then later, we'll have to engage whatever outputs we get from the subsystem to our graphic code. So I'll show you how that works as well. So here we have, I'll go to our turret swerve subsystem. So in our turret swerve subsystem, first thing I want to show you is our set turret demand. It's right here, quite plain, plain and simple. It's just an assignment, and we're taking the absolute value of it and limiting it to 1, just so as to just limit the magnitude of it to 1. And then obviously call the signum again, because the absolute value gets rid of the sign, and we need to retain the sign so that we don't just have power going in the positive direction. Now that's how we take in inputs. Now the simulate method is what this is where all our differential equations and our integration takes place. Those are all the formulas I showed before. Once again, it's just a simple copy paste. We have our time management once again over here. We actually use nanotime for this one because it's more precise. And of course, to convert it to seconds, we have to divide it by a 1 billion, because that's 90 zeros, and nanoseconds are 10 to the negative 9th. And yeah, same thing last time, current time. We showed you how to do that in the threads. And then finally, the way that we actually read outputs from this is through like get turret theta. And you can see here that we call get turret theta. If I go to this and I go to find usages, then I can take you to this one over here. Okay, well, maybe that didn't work out very well. But if we go to the turret swerve animation, as you can see, it's called over here in the cycle, and this is where we update our turret theta variable. So it's constantly monitoring the simulated turret theta. So now, not only do we need to just output like where the turret is currently, but we need to provide some inputs to it. So the one example I'll be showing you is how we can set up a PID controller with it. So we have our own inbuilt Frog PIDF utility that'll also be incorporated in our code, so you can take a look at that. But here are our PID constants. Currently, they're all set to 0. That's why it's not doing anything. But to simply explain the way these work in the slides here, the PID works such that your error with respect to time, right? Your error is something that will be updating dynamically. That's why we're considering these all with functions of time. But your error is just how far are you off from where you want to be and where you are right now. So don't think of it as like a negative thing like error, but it's mainly just that distance, is that exact definition. So proportional means that we have this constant over here that's constant, that's just making it so that the higher this error is, the more power we're going to give to the motor, right? This will calculate our PID control variable, or our overall gain, right? Because we calculate individual gains here, proportional gain, integral gain, and derivative gain. But that's our proportional gain. That's the simplest one. Now, this will result in a little bit of an oscillation. I'll show you what that means in a second here. The derivative is usually what takes care of that oscillation because it tracks the rate at which you're fixing your error. And then the integral is what will take care of any last minute, like, oh, we're still off by a little bit. My proportional and my derivative is really not doing much for me. I need that little last tiny bit of juice to get myself to where I finally need to be. So now I'll give you a quick visual depiction of what it looks like to, like a easy rule of thumb when it comes to tuning PIDs. So over here I have my whiteboard. If I had like a graph of my position, this can literally apply to anything. So if I had like my target be up here, right? And once again, this is like a position graph, so P. And then this is respect to time. So if I start out at 0 over here and I want to get all the way up here, here's basically the graph that people go by. So to describe what's going on here is this first step is proportional gain doing most of the work, which gets us all the way up here. It's like kind of the thing that initiates this full blast to the target process. But this usually results in overshoot and oscillation, because if you give it too much power and it doesn't die down fast enough, then it'll just keep going back and forth. So the thing that we put in to take care of that oscillation is our derivative constant. So that's what your derivative does, as I described before. So usually if you see a lot of this going on, you need to increase your D a little bit. That's supposed to be an up arrow. And then lastly, we have a really nice one here called the I integral. The way this works is it's constantly taking a summation of your error. So if your error is like marginal, but you want that to be fixed, then I is the trick for you, because it will constantly be incrementing, even the small amounts. It will constantly be accumulating that error, and eventually it'll get large enough such that the power is enough to overcome inertia or its stall power, such that it reaches that position. So our frog PIDF takes care of all of that through this code by calculating the output. Once again, it takes the derivative over here, it takes the integral over here using the same assignment operators I showed you before. Well, you don't need to know all that. All you guys need to know is how we take in the sensor state to determine the gain that we need to approach our target position. And that's all listed over. I think it's up a bit, sorry. All right, yeah, we define our PID constants over here. And then here we have our calculation of the PID gains by saying set point, and then we set the turret demand equal to this. Okay, so now to actually tune our PID constants, I'll quickly show you the ones that work. So because they're all set to 0, it didn't move at all. But now if I quickly show this, hold on, sorry. I'm gonna quickly stop share and make sure I'm sharing with like good quality. Okay, so if we share this over here, as you can see, it rotated to the position, but then it oscillated quite a bit. It's targeting the gold right now. But now if I add a little bit of D to it, it gets rid of the oscillation. Okay, so that's just one example of the way that we have like used the simulations to test our motion control, and the way that we actually determine which position to lock to is done in this method down here, which is like get turret lock direction. It's some pretty complicated like trigonometry. I wouldn't really consider it necessary for you to know, but like it's not complicated in its in its breadth, but mainly in the way that you have to like kind of trial and error it in order to figure out the amount of drawing that you kind of need to do on paper to make sure that you're actually getting these to map in the correct direction. But what this allows us to do is get the turret to point directly at the target that we're trying to go to. So if I uncomment this line, which gives us a projection from the turret, it's kind of like part of the turret shape, but it's mainly just a line that extends way out of the screen. And it allows us to show us how far off we are. So as you can see, we're pretty close to the target here. And if I use my WASD controls, I can move the robot around, I can rotate and whatever. And yeah, the main reason it makes determining the direction is a little difficult is because the turret isn't at the center of the robot, so it moves in a circle a little bit when you're just rotating. But just another thing that's beautiful to see is that the robot is actually accelerating and ramping down like as it normally would in an actual game. Okay, so now I'm going to hand it over to Cameron, and he's going to show you how we've used this example into our in using actual real-time sensor inputs.
All right, let me just share my screen real quick. Okay, so that was all, like raw simulation stuff. And this is taking it a little further by integrating some real-time inputs. So it's not fully a simulation at this point, but it's still mostly simulation. And the way we're taking it further is by integrating something called Chameleon Vision. If you don't know what that is, it's free open source vision targeting software for FRC. It's very similar to what runs on Limelight camera modules. And the nice thing about it is it can be run off Windows PCs, or you can run it off coprocessors like Raspberry Pis and NVIDIA Jetsons. So you're able to run it on your robot if your coprocessor is connected to the Rio. So just to quickly explain what this means, our pipeline data is based on the parameters that we set in Chameleon Vision, what it detects, and then it sends whatever it detects to the network table server, like the coordinates of whatever target it's detecting. And then that network table server is hosted by the Chameleon Vision client, which is a runnable jar file that will run on your PC. And then what we have to do is we have to change our code from just a normal Java project to actually being a robot project. We'll go into that later. But what that allows us to do is run a network tables client, which will actually let us receive data from the camera in our simulation. And we receive that data in our vision class. And then from there, we start animating. And we actually end up calling our animation in the robot.java instead of it being the main class. So to get network tables communicating on your device, the easiest thing to make that happen is to utilize WPI Lab's extension feature, which is Simulate Robot Code on Desktop. So if you translate your project over from a regular Java project into a robot project, so you'd have to create a new project and set it up as if a little more as if it was a robot, then you can actually do the simulate robot code, and it'll let you communicate with network tables. And you also have to create a class for your network tables input. So in our case, it would be Chameleon Vision. I'm not going to go too much into detail about this, but these are the equations that we used to calculate the field relative position of the target. So when you're detecting the target from the camera, it's going to be seeing it relative to the robot. But for our simulation purposes, we want to know where it is relative to the field position. This is because when we're not trying to actively update the target position, we want the robot to be able to drive to the target. And if we don't have the field position, the robot's just gonna kind of be like a dog chasing its tail, and the target is going to move with the robot when it tries to drive through it. That kind of relates back to some of the graphics translation to rotation chronology stuff that Josh was talking about earlier. And this is, it looks kind of complicated, but it's just basic trigonometry, where if you take the sine of this known robot like vision angle and then multiply it by our hypotenuse, which is our estimated vision target distance, then we can get our X and our Y values. Then this is the calculated relative position of the camera on the robot. I won't get into this, but it's another equation. And then to get the actual field relative target position, then we just sum these together, and we also add in the robot X or the robot Y. And these are some code snippets that are actually where we're doing this instead of just the equations. So what we can do is we can implement this data and we can create a basic closed loop control system where we take that data that we receive from the camera and we can drive to the target on the field. This is a super simple example because it's just a basic if statement. This is right after some of the keyboard input stuff that we have in there for like the WASD and rotation control. And it just checks if you're holding the spacebar down, or if you're not holding the spacebar down, then it's going to, based on if the target position is above or below a certain threshold, it'll send a drive command. This is a great situation where you can kind of go further on your own. And instead of if statements, you can start to teach about more complex closed loop control systems like PIDs. And I'm going to do a quick share of what that simulation actually looks like when it's running. I'm going to have to turn my camera off because the Vision client needs the camera to run. Sorry, 1 second. All right, here we go. So once it's active, you'll notice a couple things are different. One, you can see the robot was just trying to drive to the target, which is default set to the top corner. But once I hold the target up to the camera, you should see that it's updating the position on the field. And when I move it closer, it gets closer to the robot. And when I move it further away, it gets further away. It's a little janky because the values are fudged to be larger so you can actually see the difference. But once I let go of the targeting button, the space bar, it'll drive the robot towards the target. And like I noted earlier, it doesn't account for rotation. And that's the kind of thing where you can start working with PIDs and stuff like that to kind of go further on your own. All right. And with that, I think we're pretty much done.
Okay, so perfect. We actually have a question from the chat, another question we have to ask. So do you guys think you're ready to handle those, or you just have anything else to say?
Yep, go ahead. We're open to questions now.
Okay, so one from the chat would say, what is the IntelliJ theme called?
I mean, okay, I'm using Material Dark, but I had to adjust the settings quite a bit because otherwise the stuff starts to look a little weird. But yeah, I'm just using the default Material Dark, I believe. Yeah, no, Material Darker, sorry. Yeah, it's called Material Darker. I'm not using any of the other weird like recolors, but yeah.
Perfect. You think you're ready to move on to the next question?
Yeah.
Good. And so the second one would be, would you be able to take in sensor input from something other than the Chameleon Vision?
Yeah, so anything that you can create network tables data output on is something that you could take in censored input from. So if you're, let's say you have like a LiDAR connected to a Raspberry Pi, if you have that connected to your computer and it outputs network tables data, then you can still connect and receive data from that through network tables.
Perfect. Actually looks like another question rolled in. So let me just ask that real quick. Why does chronology matter in the graphics transformations?
Okay, so the reason that chronology matters in graphics transformations is when you're talking about like mechanisms that are attached to other mechanisms. So with the example I introduced with the turret here, the turret will be attached to the robot. So every single time the robot rotates, everything after that point has to rotate as well. So that's why we put the turret to draw, the draw polygon for the turret after that rotate and after the robot. But for the turret, for rotating the turret as well, it will basically rotate itself on top of the rotation that's already done by the robot. So we have to make sure to call that rotate right before we draw the polygon of the shape of the turret. So that's why we don't call the turret rotate far earlier, because the graphics makes it so that all those transformations have to be done through graphics. So anything that you do on those graphics will be transformed in whatever you've specified.
Beautiful. And that is very interesting. But going on to our next question, actually, they ask, do you plan on releasing the simulation anywhere so we can play around with it?
Yeah, if I quickly, actually, I don't have it open up anywhere. Yeah, Cameron, if you want to screen share again, we have like the link in our presentation. We can't really, if we could get someone to put it in the live stream chat, that would be cool too. But for now, you can honestly just take a picture of that link. It's pretty straightforward. Or honestly, if you can navigate through the slashes, you can pretty much just find it. If you go to github.com, you go to you search up our organization, FF503, and then you should see that repository titled Turret Swerve Simulator. It has our latest public release.
And on that note, we don't have the vision stuff in there right now, but if you're interested in the vision stuff, we'll be posting that in the near future.
Perfect. Well, I guess saying thank you for releasing such an amazing program is in order. I'm assuming the entire chat would be very helpful too. Or well, thank you from the chat would be expected.
Yeah, thank you very much for hosting us.
Well, I think we actually have one more question in order. So, well, if you'd like to go, I mean, I wouldn't want to hold you, but
yeah, no, of course. Go ahead.
How could one convert the kinematics to a tank drive?
So the kinematics that we show here for a swerve drive are actually quite simplified, although it would seem like the swerve would complicate things more, because it follows the same exact transformations that are already built into Java, which is just translating and rotating. However, for a swerve drive, you will have to figure out a way to actually rotate the robot around the point at which it's translating. So it would kind of be like how we rotate the turret on top of the robot. So rather than constantly like, and then also constantly, instead of translating with relative to the field, because you have a tank drive, you'll have to actually adjust to like robot relativity. So you'll have to take whatever WASD controls that you take in and kind of like, you'll have to do some trigonometry to basically project the vector in the direction that it will actually take place with respect to the field.
Cool. And just as a quick statement, I just wanted to say that we made sure to have someone jump on, as you said, getting that link into the chat. So I believe that it's being done, close to being done. So,
all right.
Yeah.
Okay,
and
thank you.
I was also told that there's a bunch of compliments. I'm assuming there's a bunch of people thanking you guys, saying that you're amazing, of course, for an amazing presentation. Yeah. So I guess with that, do you want to give it an extra few seconds for any last statements from the chat? And I'll just check in.
Yeah, sure.
But I'm assuming we have nothing, so I guess we'll just do a small fluff piece. So what really brought you into being a programmer, I guess?
Well, I remember my first FOL experience just being super excited about like how I was actually able to move Legos around, because I remember this is before I even understood how motors worked. But like once I finally got behind like the computer and figured out like how easy like I could figure out blocks programs, it was like putting puzzle pieces together. Like I realized that making things like making human tasks run automatically through the use of a robot was just something that really interested me. Like it makes things more efficient, more accurate. And the ways that I've seen that, especially as I've gone through the progression of programs where the sensors become better, the motors become better, and obviously your knowledge, as you learn more, you become a far better programmer. You learn the different ways in which you can control your robot to work far more efficiently and just produce amazing results. And I think that's just something great for the future of our society.
Okay. And Cameron, do you want to say yours quick too?
Yeah, I think my journey also started along with FIRST and FLL. I did FLL for a year, and I think that's what really piqued my interest in programming and just robotics in general. And ever since then, I've been part of either FTC or FRC team and been involved heavily in the programming. I think it's just a really interesting way to think that you kind of don't get an experience in any other aspect of robotics or really anything else.
Okay, cool. And I guess with that, it's time to almost wrap it up. So I just want to thank both of you for an amazing presentation. I mean, I know learning calculus, like I've learned some calculus, and then sitting here, I know I probably already said 3 times, 4 times, so being non-tech and then hearing about like the calculus involved and all the programming, and I was queuing into all of it, and I was like kind of understanding it. So I think it was a very well prepared and put together presentation. So thank you very much for coming out and giving such a great presentation.
Right. Thank you.
Yeah,
and
thank you.
125 for hosting.
And with that, I'd just like to thank everyone in the stream for being with us for the past 3 hours. I know a lot. I've learned a lot, and I hope that all of you have as well. And I'd like to hand it over to our friends, FRC Team 5985 Project. Okay, I apologize if I did this wrong, but Bucephalus from Wollongong, Australia, will be hosting the stream for the next shift. So thank you, everyone. I think that concludes our time. So thank you.
If you can build a robot, you can help a team build a robot, help 10 teams build a robot, help teams in every continent. Well, maybe not Antarctica. If you support girls in STEM, connect girls around the world, break that glass ceiling, shatter it. If you can use your phone, create a Google Hangout. Use that Hangout to assist teams from around the world. Get other teams on board. Do it 24/7. If you can program a Lego robot, you can run a RoboCamp, run a small business, make enough money to run a team, franchise it.
Oh, so you want me to leave?
So, are we ready to begin? So, g'day, guys.
Cheers. Hello.
Yeah, sure. Do you want me to share my screen now?
So, are we ready to go? So, we've got 1678 talking to us about scouting. Is that correct?
We're talking about pneumatics and power transmission.
There we go. We got the wrong one. So, g'day, guys. We're speaking to you from Australia. Where are you guys at the moment?
We're in Davis, California, in the United States.
Okay, so are we all ready to begin, do you think? What are you going to lay on us today?
So our presentation, we will be talking about pneumatics and power transmission and kind of how that works with design. I'm Ellie Bukowski. I'm obviously from Citrus Circuits, and this is my third year on the team and second year on the design sub team. Zach, do you want to?
And I'm Zach. I am also a junior on 1678. And this is my third year on design.
So I should have done a better job of introducing your hosts for today, so apologies for that. So I'm Andrew. I'm the lead mentor of 5985. I've been doing FIRST since 2010. This is Stella.
Hey.
She's just started FRC.
I'm a rookie.
And we have Bella, who's going to be joining us shortly. So if you're ready, take it away.
Yeah. Nice to meet you. And yeah, okay, so. Whenever you're. All right, so the first part of the presentation we'll be talking about designing with pneumatics, and this covers compressed air, pneumatics, the Clevis, as well as our FRC applications, and generally designing with pneumatics. So compressed air is, of course, used in every sort of pneumatic. That's how they are powered and controlled. And these can be controlled on board or off board. So that means either on the robot, you can have a compressor actually compressing the air, or you can have it in your pits and just have tanks of compressed air. Having them on board will allow you to have constant compression throughout the match. Like if you don't have enough tanks of air, you can always generate more. However, this does require weight. So it's kind of has its pluses and minuses. You're only allowed to have 120 PSI in the tanks if you do have tanks of air on board, and a 60 PSI working pressure. And this will not drop until you get below 60 PSI. So you do have quite a bit of pressure in there. So it's not too much to worry about to just have tanks on, but you could have a compressor as well. So next slide. So here's some like general information about pneumatics. They provide a linear motion between two positions, kind of that in and out position that you can see there on the screen as these two are demonstrating. And these are effective for actuating arms as well as providing kicks, which you will see later in our presentation in our examples. And the force can be calculated by multiplying the working pressure, which is usually around 60 PSI because that is our limit in FRC, and by the area of the cross section of the bore. So that's kind of that cylinder there. And as you can see in that bottom image, this does release air with every actuation. So when it goes in or when it goes out, it's releasing air. So that's important to keep in mind. So now a little bit about the standard Clevis. So you can see that's kind of that little piece there that attaches to the end of your piston. Yeah, circled by red that Zach is pointing out. And this is attaches at the end of the rod. This is actually kind of a complicated process to make one of these. You have to cut it down to size on the lathe, and then you have to drill it out using the lathe, and then mill the top hole and then tap out the inside so that it can screw on. So it's kind of a lot of work for just a tiny piece, but this is important for mounting onto your mechanism so that you have those two mounting spots for your piston. Okay, you can. So here's some pictures of our FRC applications. You can see there to the left, our hopper intake, where you can see the pistons on both sides. And those are for pushing out the top part to intake and then having it tuck in when we're just driving around the robot. And then you can see on the right, that's kind of our arrowhead for the 2019 CompBot. And that would have one piston to push out and then a couple more pistons to push the little arms out to stick the discs. And this, so you can see that there's kind of multiple uses there for that, the pistons. And then you can see here, this is our shooter, I believe, for our CompBot. And this, you can see the piston right there, how it pushes the wheel in and then it can pull it back out. And this is an example of a kick, just like the picture on the left in the previous slide. Okay. So then just some considerations to take into account when using pneumatics for designing. This is a pretty good example of, I believe, a well-made piston kind of configuration. You want your back part, that back part where it's mounted, to move as little as possible. And because if there's too much rotation of the rear pivot, this will reduce efficiency. And it's important to have, for arm actuations, pneumatics mounted to those pivot places, which you can see kind of there, where the clevis and the back part is mounted. And the longer the pneumatic is, it takes up more space, which can be a concern on our small, like they're not very small, but our robots, where you are taking every little bit into account. But it is important to have this further mounting point away, because if it's too close, it will increase the amount of torque on the system, and you want to minimize that as much as possible. And this will just create more of a mechanical advantage. So here's kind of like a wrap-up slide for what we've been talking about. You can see there in yellow is the piston in its in and out positions, and those blue circles there are the clevis mounting points. And you can see how the green and red lines, they're the same distance. And this is because the in and out piston, when it's in and when it's out, has to be the same distance from that mounting point for the piston to work correctly. So this is kind of just like a basic, when designing a piston, make sure you have those points in the correct positions. And okay, so just to wrap this section up, some little tips on when designing. It's important to have that 1/8 of an inch space that you can see there on the top image when it's all the way in the retracted position between the clevis and the cylinder. And then the clevis motion should be defined by a cylindrical or slider mate. So this is like when you're using CAD software, make sure that you have that mated correctly, so that it doesn't just go anywhere and that it only stays in that linear position like you want it to.
All right, so now we'll move into a section more on FRC motors and on power transmission. We'll be talking about converting power to motion in motors, and different forms of power transmission and considerations to take into account when designing mechanisms with these power transmissions. So just some common motors in first. Some of the most common ones are sim motors and mini sim motors, which are fairly comparable motors with exception to a few things. They have very similar free speed, which makes them pretty interchangeable. Unfortunately, sims are a bit heavier, but they can also stall out for a lot longer without burning out. And mini sims give out about 2/3 the power output. But because of their interchangeability in free speed, we generally go with mini sims just because they are a lot lighter. They're actually motors that we use that we would use most commonly on our drivetrains almost every year for the past few years, except for this past year. We've had a drivetrain with some gearboxes with 3 mini sims on it. There's also 775 Pros, which are on the much smaller end, as well as back motors. But 775 Pros have the same power output as sims, but are significantly lighter. They're a lot nicer for low load mechanisms like intakes, but unfortunately they do burn out quite quickly when installed. And then just some newer motors that have come out in the past couple years. The Falcon 500 is a very nice motor. It's a brushless motor, and it is comparable to the Sim in many ways, except it is more powerful, efficient, and is a little bit more lightweight than both the Sim and Mini Sim. Another plus for it is that it has an integrated speed controller and encoder, so that you don't have to worry about putting those elsewhere on your belly pan or somewhere else on the robot. And there's also less needed per mechanism because of the fact that they're more powerful. For example, this year we used Falcons on our drivetrain gearboxes, and whereas previously we had used 3 mini sim gearboxes, it used 2 of those. This year we used 2 gearboxes that had 2 Falcons each. There is also the Neo 550, which, similar to the 775 Pro, is really nice for low load mechanisms. Brushless, it's a brushless motor, very compact. I don't know if you guys have seen them before, held them. They're very, very small, even compared to the 775 Pro. Yeah, again, they're very, very nice for low load mechanisms. We used them on our first iteration of our intake this year. With the motor basics here, there's some power equations and conversions here, but what you can mostly focus on is the actual layout of this of the motor here, because this will explain a little bit of what's to come in a second. But this is the housing, which is what you kind of see on the outside of the motor. It's that just case that holds everything inside of it, that's stationary. Inside of that is a spinning rotor, which has the output shaft sticking out of it. So for brush motors, if we go back to the housing here, you can envision envision it in a brush motor as a form of a sort of magnet, stationary magnet, meaning it has a north and south end to it. And then there is this coil that you see here, which you can just say this whole thing is kind of a circuit that it's making. And the coil, along with these commutators, which are these semicircles here, are the parts that rotate, and they slide up against these brushes here. So when a current is sent through to these brushes, they are contacting the commutators, and they make a complete circuit with the coil. This circuit is aligned in a certain way so that the charges of the coils, the polarity of them, makes them want to naturally flip to the opposite end. So that means this would have like a north end, and this would have a south end, and they're trying to flip to get into position for that. But then about halfway through, you'd see how there's kind of a slot right in here, which divides the two commutators to be contacting the different ends of the coil. When this flips to that certain point, it will actually flip the which end of the coil that that current is going through, meaning that the charges of this end and this end of the coil have just flipped, which kind of sends it on that loop where it just keeps seeking to reach the other end of the motor housing. So this is a simplified model. This is what an actual motor will look like to avoid any dead spots and to keep constant torque. These commutators are kind of chopped up into a lot of little ones just like this, how you can see all those. And each one has its own like coil, so that each coil kind of has its own turn, being the one trying to reach the other end. And this keeps torque consistent. And also there are multiple cords, wires added in per coil, as you can see in here, which just increases the strength of the motor in general. So for brushless motors, whereas in here, the stationary magnet was the exterior of the motor, in brushless motors, the stationary magnet, the permanent magnet, is the rotor in here, and the electromagnets that are triggered by the electrical current are the coils, which are on the outside of the housing. So basically the way that these ones work is that these coils produce, they're told to produce a charge. So you can see here as modeled, this would make a north end, and then this a south. And naturally now the magnet is trying to align itself with those. And then once it would be about to reach the green, then it would trigger the purple. And then once it reaches the purple, the orange, and so on. And then this chart just kind of, this depicts multiple different like aspects to a motor to take into account when you're going for ideal RPM and power output. The two biggest things that you should be taking into account are the power output power and the efficiency, modeled by the green and red lines here. And so as you can kind of see, they are a little bit inversely proportional here, meaning that when you're trying to get greater output power, that means you'll have less lower efficiency, which is less power going into the motor that is actually being translated out and not dissipating out into nothingness. And then if you're going for higher efficiency, that means you're getting a lower output power. So what you want to be aiming for is kind of the point where they intersect here. In terms of the Falcon, that means you want to generally be staying within the range of 4,000, 5,000 RPM. And yeah, that's about it on that.
All right, so now we will be moving into the power transmission segment of our presentation. So there's some general different types of methods that we use in FRC, and this is pretty limited. So it's really important to make sure that you're choosing the best methods possible. So some things that I will be going over in this next segment are 20 DP versus 32 DP gears, as well as 3mm and 5mm belts, 25 and 35 chain, and polycord, as well as planetary gearboxes. So here's some general info on gears. So of course there's the driving and driven gear, which kind of intuitively is the driving gear is the one with the power source connected to it. And then it's driving the driven gear, which is then rotating because of that. And the gear ratio is that input or driving gear to the driven gear, or divide by the driven gear. So if you have like a 50 tooth gear to a 25 tooth gear, that would be a gear ratio of 2, and then you'd have your second gear spinning at twice the speed. And there's the diametral pitch, which is DP, which you've probably heard before. And in FRC, we have the 20 or 32 DP gears, and this is important when calculating the pitch diameter or the outer diameter. And these are important. The pitch diameter is especially important because this is where your gears actually contact, and you want that as close as possible to the pitch diameter where they actually contact for peak efficiency. And the center to center distance is really important when calculating because you need to add those 0.003 inches in order for the space between the two gears to be as good as possible so that they're not too close together. Of course, if it was just the diameters added and divided by 2, then they would be like touching, and that obviously is not what you want. So some important considerations to make for gears when you are using them to model your robot is that the meshing between gears is inverse, so or reversed. So if one gear is going this way, that makes the other gear go the other way. So this can actually be used to your benefit if you want to have 2 belts going different directions, and you don't want to add another motor. You could just add a gear shift or add a couple gears to make them spin opposite directions. So that's a good use for that, but it's also important to keep in mind if you're making like a gearbox or something. So then, of course, as I said before, center to center distance accuracy is critical, and the larger the reduction, the more force is in the smaller gear, which basically means the bigger the gear to the smaller the gear, there's going to be more force in that smaller gear. It will be spinning faster, of course, and so that's important to keep in mind. And the higher the chain in the higher in the chain of the gear is, the less force is. And as you can imagine, each reduction loses efficiency. So every time one gear transfers energy to another gear, or moves a driven to driving gear or driving to driven gear, that's going to lose efficiency. So try to minimize that as much as possible, of course, with other considerations. And gear shaft slop is another thing to keep in mind. This is kind of like how your shaft is rotating compared to your gear. And so you should be using hex shafts whenever possible in order to make sure that your gear and your shaft are rotating the same amount and there's no loss of control or efficiency within that. And of course, keep everything lubricated. Make sure that it's not because of like other reasons that your gearbox isn't going as smoothly as possible, of course. So now moving on to chains. I said before, there's 2 different types of chains, the 25 and 35, which have a 0.25 inch pitch and a 0.375 inch pitch. And you can see there in that second image, that's kind of the distance between those rollers. So it's important to keep that in mind when you're choosing your gear. 35 inch chain, or your chains, 35 chain is usually stronger, but like heavier, so just keep that in mind. And then of course with your chains you want to choose the correct sprockets. So this, you can see those top 2 images, there's plate sprockets like in the right image, or like ones with hubs like in the left. And the hub is kind of that part that extends out from the sprocket. So, and then of course the bore type, if that's a hex bore or a round bore, of course, depending on which shaft you're using or however you're mounting it. So some more considerations, as with any sort of system like this, you're going to want to make sure that you have a precise center distance, because chains will skip, and this is important to minimize in order to get your peak efficiency. You don't want loose chains, like that will really mess with your system. And the best way to make sure that you have peak efficiency in your system and that you're getting that as tight as possible is to add a tensioner, such as a cam and a slot. So like some sort of thing to keep it as tight as possible. Yeah, you can see kind of there in the bottom, there's like cams there to tighten those. And there's better examples on other robots that you can see in some of our previous robots. There's good examples of tensioners that you can use. This does take up a bit of space, but I'd still recommend using it because it really helps with efficiency, and you should be checking that every time you go into your pit. Like, you should be checking, making sure those are as tight as possible. So your chains are at peak efficiency. Of course, avoid using things that will break, master links or links, base anything other than a normal link, just to keep it as solid as possible, because of course no one wants their robot breaking in the middle of a match. So belting is, of course, it's similar to chains, where you want, it's a belt rolling, going around another thing, such as like a sprocket. But so there's two different types of belts that we often use in FRC, and that's GT2 3mm belts and HTD 5mm belts. And the 3mm and 5mm basically refer to the height of the belt. So 3mm, or the teeth. So 3mm is shorter teeth. And you can see there, it's like in the picture, it has that curvilinear profile, or it's like kind of rounded to fit like within to mesh better. And this provides better contact and indexing. Whereas the HTD 5mm belts have that thicker, like longer teeth, so that they are stronger, which makes them in turn better for high load applications. If you want to make sure you're choosing what's best for the right application. So kind of to wrap this segment up, I'll be discussing VersaPlanetary. So there are definitely pros and cons to VersaPlanetary. So it's not like every single situation. You don't want to use it for everything. But one good thing about VersaPlanetary is that it has very high reduction in a small space. So you just have, so you can kind of see in that bottom left image how it works within the VersaPlanetary. It's basically a lot of tiny gears rotating around what seems like basically gear teeth, but like in a circular area. And so you can have all sorts of different reductions. It's definitely highly modular and easy to assemble. As you can see here, it comes in 3-to-1, 4-to-1, 5-to-1, 7-to-1, 9-to-1, and 10-to-1 reductions. And these can be stacked up to 100-to-1. So it definitely has a lot of different reduction and variability depending on what you want to do in this situation. And it has no complex design, which is great. However, this cannot be used in every application because, unfortunately, because as you can see there, there's such tiny gears that they are really not very strong. And a high reduction means a lot of inertia, which means that your system is going to want to keep moving even when you try to stop. So this can like be hard for your system. So make sure that you're taking those into consideration when you're adding VersaPlanetary to whatever you're doing on your robot.
All right, so this is kind of our final part here, but I'm going to be talking about like when you are selecting transmission types, what is best for what scenario. Obviously, there's going to be a lot of variance in what will be the best in whatever case, and a lot of it will come down to judgment. But you can take a lot of these into consideration. Reduction, adjustable distance, strength, and the directionality of the transmission. So first off, there is reductions. And so as Ellie was talking about earlier, you can make reductions by having a bigger and smaller gear, sprocket, pulley. And now the one thing with stronger like teeth sprockets and gears, like a 20 dp gear as opposed to a 32 dp gear, is that the pitch of those teeth, the teeth being so thick compared to a 32 tooth gear, makes it so that making a big reduction takes up a lot of space. For example, this might be a 60 tooth 20 dp gear. But in the same circumference, you could probably fit a 32 dp gear that has over 100 teeth, meaning that with a certain amount of space, there's a lot bigger of reductions that are possible with these things that have smaller pitches. So this also applies for a 3mm belt as opposed to 5mm belt, and number 25 chain as opposed to 35 chain. And with polycord in general, because your smaller end will still have to fit around probably at least a 1-inch diameter, it takes a lot of space to make a big reduction with polycord. So another thing to take into account is whether your transmission type has an adjustable center distance, because for gears and for versaplanetaries, they actually don't. With gears, obviously, because there's nothing wrapping around the two, you can't just move their center distances far apart and make that thing longer. You have to, if you're going to move their center distances apart, you would have to actually expand the both gears. And the downside to that is that when you are with something like chain, for example, if you are just expanding its center distance, you are really doing nothing more than that. You're just making that center distance bigger. But with gears, when you have to move them apart to increase the center distance, you're increasing the whole circumference of both gears, right? Because you're expanding them. So you have to increase the actual circumference of both gears. So it eventually takes up a lot more space, and probably just won't work out as well as something like chain or belts. Versaplanetaries also, as Ellie was talking about, they are all in that one like casing size. You can swap out what's inside them, but there's not really any changes to this size or the distances between those, just because it's made up of a bunch of gears. And then additionally, one thing that these that chain and belt can't do, that polycord actually can do, is polycord is able to be any length whatsoever, any center distance that you want. Whereas with chain, as Ellie was talking about with the links, it's the growth of a length of chain is incremental. You have to add one link at a time. And so that makes it so that your center distances, if you have to be very exact with them, it can be difficult with something like chain or with belts, which generally in COTS only comes in increments of 5 to 10 teeth too. But with polycord, it's flexible in how long you can make it, just because you're cutting a piece of polycord and putting it together. But there's also another thing to take into account, which is strength and torque. When you have bigger teeth on both the chain and sprocket, or on sprockets and gears and pulleys, it makes it so that you're gripping more to the thing that you're turning, which in turn is giving you more strength. This means that when you're making something like a drivetrain gearbox or a climber gearbox, we will almost always, for every single gear in it, they will be 20 dp or bigger, because 32 dp has a tendency to grind away quickly under high loads. So we only use 32 dp where we can't use a 20 dp, maybe on some output pinion. But that is something to take into account, is that on things such as, for example, also our 2019 wrist, we made sure that we were using number 35 chain for that wrist, because of what a heavy mechanism it was to be lifting up and down. So we made sure that we were using just about the strongest power transmission possible. Another factor in everything is the directionality of your transmission. Gears, as Ellie said earlier, the driving gear and driven gear will actually go in opposite directions. So to make those go in the original direction again, that would mean you would have to add in some kind of third stage or whatever. Then for things such as belts, they only go in the same direction because they're carrying that belt along in the same direction. Versaplanetaries as well, just because you have all those gears rubbing against each other that all fall into the same direction. And then with chain, it's difficult to make them go in a reverse direction, but it is possible by basically implementing kind of a system with a tensioner sprocket to make that one be the driven sprocket. That would be one way to make them go in opposite directions. And this is another place where polycord is really nice. Actually, I'll go back all the way to our 2019 intake here, where we actually used polycord in a flipped state because we wanted to be sucking up the cargo balls from against the floor. So this meant that these rollers are going clockwise like this. And we also found that it was helpful to have this roller at the bottom go counterclockwise. So we were able to drive them both off of the same Versaplanetary by belting off to these rollers to make them go clockwise. And then we did a flipped version with polycord, which is where you're turning it from belt style, basically, and you're flipping it into a figure 8. So it goes in opposite directions. So that was how we kind of branched one motor into two opposite spinning rollers so that we could suck up cargo balls really well. And then let's see, where are we? Right here. And that's about it on directionality. So for what we would choose to transfer power from wheel to wheel on a drivetrain, we normally use number 25 chain. because it is low profile, so we can fit it in our drivetrain pretty compactly. And it is also still quite strong. Sprockets and chain in general are very strong. The one downside to them, as opposed to belt, being that they are simply very heavy, with the chain being steel as opposed to being belt. And then also with quick reductions in a small amount of space, Versaplanetaries are great. On intakes, for example, where you don't have that much space to work with generally. It's really nice, especially because on an intake, you don't need such a high load. So the torque doesn't really matter that much. Back to that example of 35 chain on our wrist on our 2019 robot. We use that there just because it is such a high torque power transmission. And just generally to reduce the output speed from anything high load, any gear, a diametric pitch which is bigger than like 20 is great. All right, thank you for listening. I think we can go into the Q&A now.
Yep, are we on now? Hi. So, oh yeah, this is Bella, by the way.
Hello.
That was really great, guys. That was really amazing. It was really clear. And oh, by the way, Bella's a rookie too. So you're talking to complete newbies. We know nothing. So that was really great. We understood all of that. That was really good.
Yeah.
We did have a few questions, if that was okay. Yeah. So we did have a few. You want to do the first one?
No, you do it.
Okay, I'll do it. So basically we did have a few, which was, yeah, there you go. So how did you decide when to use the motors over pneumatics or the other way around? So how did you decide between the two?
So generally on our robots, we'll choose to use pneumatics because pneumatics are like two position like mechanisms. They just have their retracted position and their extended position. We'll use them wherever we can, like on an intake when it retracts or extends. But for things that need like adjustable distances or just constant motion, we'll use motors. Like for example, on our hood for this year, which had to go to multiple different distances to track where the goal was. So we could shoot from almost anywhere and didn't have to go to one specific spot. But yeah, we tend to use pneumatics wherever possible for those. But whenever the situation requires any constant rotation or just multiple positions, we'll use motors.
Yeah, okay. Yeah, that makes sense. You want to ask one more?
Which motor would you recommend most for low load mechanisms such as intakes?
I mean, Ellie, do you want to take this one if you... I can take it if you want. Do you want?
Yeah, you can.
So yeah, for low load mechanisms like intakes, generally we'll go with like something like a 775 or like for example our Neo 550 that we used on our first iteration of the intake this year. Just because they're lightweight and they still get the job done. Yeah, something like a Falcon, which we did eventually add in, is a little bit heavier and like somewhat unnecessary for an intake. And also, we know that like for most teams, when you have only a certain number, it's a lot like better of a choice to put the Falcon on a drivetrain or a climber or shooter, something that'll be taking a really high load of some sort. So generally, it'll be something small and lightweight, like a Neo 550 or a 775 Pro.
Yeah, okay, that's would be good.
Just to like add on to like what we've been saying in this presentation. Basically everything that you do requires like everything that you do, you have to make sure that you're under limits. So for example, weight limits for like motors, etc. And like you only have a certain number of motors you can use. So like Zach was saying with pneumatics, you want to make sure you're using those as much as possible because you don't have like too much room, especially if you're trying to do as much as possible. You want to be able to use all of your things the most efficiently and to the best of your ability. So yeah, just to add on to that.
Yeah, that's really good. We have a few more if that's all right. Two more. Just wondering, what were the different types of like links that on the person that the energy string was talking about? Oh wait, sorry. What is the difference between the different types of chain links and why do certain ones break easier? So what would
you want to go back to the slide, Zach, with the
yeah, sure.
So basically so the master links and the half links, those are kind of like, so you know, like a regular chain link, it's kind of just in that image there you can see well, you want to go to the picture of the chain, the one with the like, you can see you can see there at the bottom the links there, how those are kind of just the normal links. So the half links and the master links are just like, imagine half of one of those kind of connected, like truncated version of it, and like you can kind of imagine, or like a master link, it's like a different like sort of attachment so that it's not as strong as like those regular links, so they will break more easily because they're just not connected in the same way.
Yeah, they're less stable in a way, kind of, is what you're saying. Yeah, they don't have any kind of hold on them. Yeah. Do you have any more questions? Yeah. So in your own kind of, when you're building the robot, obviously you've had complications this year with all of COVID and everything. Some teams are completely rebuilding robots. Some of them are just working on the ones that they already had. Have you had any problems with your own pistons and motors specifically? And how have you altered it to then allocate properly to your robot? How have you fixed it if you have had problems?
I don't think we've had too many problems with pneumatics and motors this year. I know what we like started using Falcons this year, right? And those are those have been like really, really good. And we've put them on a good number of our mechanisms, and they've performed very well. But I don't think there are too many. I know we eventually took out the Neo 550 on our intake just because we decided that we didn't really want the motor to be on the part of the intake that was moving in and out. And we found a way that we could put a motor, kind of fit it within the robot and then belt it up and over to the intake. But I don't think there really have been that many performance issues we've had.
Yeah, we've been like very lucky to have very good mentors who are always there to like help us and make sure that we are kind of trying to use the best things possible, and you know, more experienced students to help as well, which has really been good for our team in order to have our robot like kind of as good as possible, just to have that experience and help. So
Yeah, that's really
avoid
good.
issues.
One last one, if that's okay. So you did mention you prefer pneumatics, which we get totally. We prefer them. I said we prefer pneumatics as well. Although when it comes to brush motors and non-brush motors, which one of those would you probably go with?
I think we normally go with brushless motors are a little bit nicer, just because well, they're more compact because the actual like I guess sorry, without the brushes kind of sticking out of the back, those what kind of replaces the brushes go in a space that was kind of occupied before anyway. So they're a little bit more compact. And also, I know that brushes sometimes can fail and have a little bit like the maintenance for them can be like something to worry about. So I think generally brushless motors just operate a little bit better and have longer like lifespans too. Yeah, I think that's about it on that. Like brush motors are still really good. I think brushless motors are just a little bit more efficient and have a longer lifespan.
More reliable.
Yeah, a little bit more.
We think that too, actually, probably.
Yeah.
Although, again, I joined this year and we've got some other experience. Do you guys do FLL as well? Or maybe
we have a program similar to that using Vex Robotics called our Davis Youth Robotics program. It's pretty similar to FLL. It's just that it uses Vex IQ, which is again like kind of similar to Legos. They make robots of similar sizes, and they have a big game field every year, just like FLL. But
yeah, see, because I've done that, and Bella, you've done it too, yeah? I'm still doing it. Yeah, you're still doing it. So I'm going to be too old for it if I keep going. So I do programming outside of this. Other than that, I don't know anything about robotics. So it's really nice that you guys explained it so clearly. That was really good. We just got more questions. Sorry. Do you want to say this?
Which one?
Do any of them.
Okay. How close do the gears have to be so that the gears don't scrape against each other?
I think our general rule for that, let me see if I can find the slide again. But we generally add 0.003 inches. I don't know what the direct conversion to centimeters is right now, but we add that amount generally because we do notice that when we just have the center to center distance by itself, it does cause a lot of grinding, even with like proper lubrication. So yeah, it just add not much, but like just a little bit to that, about 0.003 inches.
Yeah, that's good. So that they don't make the teeth uneven to each other, if you know what I mean. In what length do the chains have to be to help the gears so that they stay together? Do they, like, not to lose how tight it is? Like, not to be too tight, you know what I mean?
Sorry, can you repeat that?
Yeah, that's okay. I said that wrong anyway. In what length do the chains have to be to help the gears stay together? As in not too loose, not too tight.
Oh, like how tight you should have your chain?
Yeah, yeah.
We actually for chain, we don't normally set like we'll normally find the center distance, like just kind of measure it with calipers or calculate it some way like that. But we normally have tensioners just because that does tend to happen sometimes. So a lot of the times, a lot of the like chains that we use, we'll have our two sprockets and the chain going between them, and then we'll just have another sprocket that's like contacting it, and it's on a slot, like it's fastened to a slot, so we can slide it in and tighten it, just to define that dimension a little bit nicer. Yeah, it's most of our chains will have some form of tensioning. So we don't really have too much of a rule on that. It's more just on the feel of it, I guess.
Yeah, that's good. That's all right. Oh no, that's all right. But we do have. So you guys are supposed to talk till 2, yeah?
I guess 2 your time.
Oh right, I'm stupid. I keep forgetting. Sorry, I keep forgetting that this is not just in Australia. Oh gosh. All right. No, that's really good. I don't think we do have one last one that won't take too long to answer. When do you use a gear stage over a belt or chain stage? Do you?
Yeah, we'll use gear stages. Normally we prefer gear stages if it's possible. But gear stages do have to be a certain distance apart. They have to, or like within a certain distance before it gets a little bit like ridiculous how many gears you'll need to make the actual transmission. So they do have to be within like a few inches of each other for us to use gears, but we will generally prefer gears in those instances. Yeah, chain and belt we'll use just in longer cases, or if the rules that we were talking about how gears flip each other and belts and chain don't. You can go by that, but also just if that part doesn't matter, then yeah, we'll generally go with gears if they're close together, and chain or belt if they're far apart, and respectively like on between chain or belt. That'll just depend on the load. Like belt you'll use for anything that's low load. It has a really good efficiency for things like that. And it is very, very lightweight, as opposed to chain, which is like steel. And so, yeah, we'll use chain whenever we need anything high load, but low load, you'll go with belt if it's fits those like long length requirements.
Yeah, that's great. Thanks so much, guys. It was really cool talking to you. I know it's your last day, so it's really nice. It's really good thing to you. So thanks so much for the presentation. That was amazing.
Yeah, thank you so much for having us on.
That's all good. Have a great day, you guys.
All right.
All right. Bye.
Okay, everyone. So that was the end of the energy stream for today. So from 5985 in Australia, we say good night, good morning, wherever you might be. Go check out the other streams and we'll be seeing you around. So good luck, everybody. And we hope to see you sometime this season. Good night.
Good night.
Good night.